Okay. Again, a good morning to those who have joined in the last minute. We are now going to start. It's 3 minutes past 10 o'clock. Welcome everybody for the second day of our second joint harmonization and standardization workshop. This time around brought to you jointly by the Macrame project, the Motor Initiative, and our sister projects Accord, iCare, and Nanopass. And we have representatives of these projects online. Some of you will guide you through the program today and be your question and answer hosts and general chair of the sessions. We will start the morning with a session on standardizing testing along the life cycle, which Blanca Suarez from the Macrame project and iCare project is definitely one of the and Nanopass, sorry, I keep forgetting, Nanopass as well, is definitely one of our experts. So Blanca will be with you throughout the morning and chair the session. And we will then hand over to our colleague Damiana from the Accords project, who will guide you through the program from late morning until the end of today at around about 3 o'clock on the essential use of advanced computational methods. So that is what awaits you today. We had already, for those of you who couldn't join us yesterday, we had an awesome day yesterday, and there will be some things today, specifically, I believe, Roland's contribution on OMICs that will pick up on some of the discussion that we had yesterday. But in essence, you can join today without necessarily having been there. Anything that needs to refer to yesterday will be repeated in the context in which you need to know. And that means that without any further ado, I can hand over to Blanca. I just realized there is this, I have this map of Europe behind me, and it looks like the sun is coming out above Europe. That is a lot more than I can tell from where we are sitting here. So great day to spend here and listen to this great workshop. Thank you, Blanca. Over to you.
Thank you very much, Steffi, and good morning, everyone. Now we will start without further delay, and it's my pleasure to introduce our first speaker, who is Anna Pohl, who is a scientist at the Federal Institute of Occupational Safety and Health in BFR in Germany. So the floor is yours, Anna.
Hello, good morning, Blanca, and good morning, everybody. I will start sharing my presentation. So you should see my screen, and now you should see it in presentation mode. Thanks for logging into this workshop. As we do that every year, it's always great fun to see how everything is evolving and how the world basically gets on a lot of different things, and I think it's good to compile that in this workshop. So my name is Anna Pohl. I work at BAuA, which is a Federal Institute for Occupational Safety and Health in Germany. We are located in Berlin. Also, like Steffi pointed out, it's gray and rainy right now. Nevertheless, we can talk about the release of nanomaterials and how we can test potential release along the life cycle of nanomaterials. I know many of you are already tackling advanced materials, but I think that some of these aspects that we are dealing here with are also useful for advanced materials. And I think it is good that we basically see these different aspects and then also see how we can maybe expand that towards advanced materials. But why are we looking at nanomaterials and at the release of nanomaterials or the potential release of nanomaterials? So nanomaterials and also products that are composed of or enabled by nanomaterials can have several steps in a very complex life cycle. Some of them may not, some of them may just be synthesized and then used for one application. But since these are very versatile and can have a lot of fine-tuning within their material properties, many of the nanomaterials are used within different steps of a complex life cycle. So we can start at the top, which is the synthesis and production of the nanomaterials, and then move to the right about processing. We could have a downstream use of course, they can have a service life because they are made for using them in the end in a product. And when it comes to the end of life, one can look at either waste treatment, which would mean that they are just dumped somewhere, or they end up in waste treatment facilities, or we could think that they also might be recycled, and then they kind of get again in the loop of synthesis or production of a new product. And within all these life cycle steps, they can be very different for some of the materials. We can have a multitude of different processes that are performed and that basically are determining what is done with the product and where it maybe end up. And when we look at these different processes, I just put them here, examples of them for the different steps that we've seen before. I tried to narrow it down to specific steps in the life cycle, which most of them go through. So synthesis and production, and then further processing, service life, and end of life. And then we can have the different processes that are performed. Of course, when you synthesize a nanomaterial, you have wet synthesis or chemical vapor deposition, physical deposition, but you can also have milling processes, you do mixing and so on. So there are several steps. And then same goes with the processing and service life. For example, if you disperse the nanomaterials in a liquid, you may do sonication. For 3D printing, it would be extrusion. But then, of course, if you embed your nanomaterial in a product, like a polymer matrix, you would have maybe sawing or cutting of this matrix in the end. Maybe there's an abrasion done because you want to have a clean surface. And then during the service life, it could also happen that, of course, the users is doing something with the product. So maybe some users is abrading the matrix in which nanomaterials are embedded. Of course, if the nanomaterial is embedded in a cloth or like a fabric, then they will wear it, hopefully, but maybe they will also sweat and they will do machine washing. So there are several steps that are done also for fabrics that are incorporated with nanomaterials. And then when it comes to the end of life, of course, in these waste treatment facilities, a lot of these items are shredded or cutted. We will have aging and weathering processes. There can be chemical reactions, and one can think of combustion when the things are basically burned in waste facilities. And all these processes, they can potentially lead to a release of nanomaterials. So that can happen, and if the nanomaterials in these is included in these products, and you cut it or you drill it or you saw it, then it basically can be released. As you may have seen, also some of these processes can happen during different steps of the life cycle. So it's not so easy to sort them against the life cycle. As you can see, some of them, they occur several times because, of course, somebody could do the sawing in different steps while the processing life cycle as service life and the end of life. Nevertheless, maybe the circumstances under which this happened is different. So maybe, for example, the user is not sawing an entire day, whereas somebody who is doing that in a waste treatment facility may do that the entire day. And then, of course, also the prevention can be different, or hopefully is different. So there are specific points that are then still to be taken into account, but the basic process actually is happening or can happen during different steps of the life cycle. And then the release of these nanomaterials is not only depending on the process that is happening, but it also has some other parameters that are important. So, for example, the initial nanomaterial that is inserted in the nano product, it can have different morphologies, chemical compositions, or surface modifications. And then we can have a matrix around. Sometimes we don't have a matrix if the powder itself is used, but many times we have different material properties, chemical compositions, and then also if it's, for example, polymer matrix, it depends on where in the matrix or in the product the nanomaterial is actually incorporated. And then we basically can discriminate between powder that is used, the nanomaterial that is dispersed in liquid or embedded in a solid matrix. So as you see, it's not only about the process that is happening and that is determining how much or how many fragments are released, but it also depends on the nanomaterial itself and also the matrix that it's included. And then when we think that the nanomaterial is released, it can also be that these released fragments do not look like the pristine nanomaterial that was included. Most likely they won't look like that because there are a lot of things going on, first of all, during the process itself, but then also during the, for example, service life of the product, it's aging, so you can have different transformation processes that are happening. So when we look at the released fragments, we can maybe find some free nanomaterial, but maybe for some of the matrices very unlikely, but instead we will have matrix fragments. We will have fragments that are composed of matrix material and nanomaterial embedded, or maybe it might be attached to it. We can have nanomaterial dispersed in a liquid, and then of course the nanomaterial itself that can form agglomerates and aggregates, and also mix with other particles or other chemicals. And also it can be transformed itself, so maybe it is shorter, maybe it is thinner, so the morphology could have changed, but also it could be some biomodification, so that you have a biofilm on top of it, or that the chemical composition could have changed. So there's a multitude of things that can happen to a nanomaterial during these release processes. So this is important to keep in mind when one wants to analyze the release of nanomaterials, because maybe those things that we are looking for doesn't even look like what is inserted before. And so why are we looking at release and specifically at release tests? So we start from the nanomaterial or the nanomaterial product, and then we have these processes along the life cycle, and we have the released fragments. But then if they get transported, this is basically the route towards exposure. So whenever release is happening, it is the first step towards exposure. And that means the exposure of occupational personnel, of course, but also consumers and the environment in the end. So for us, it is important to learn more about the release, and this we can do by performing release tests, because the release basically is one parameter that determines in the end the exposure. Of course, as I said before, we then have prevention mechanisms. We maybe have a longer or shorter duration of the exposure and so on and so forth. But basically, if there is no release of the nanomaterial, we won't have any exposure. But if there is release, then it's very likely that we can have exposure. So this is why release is an important topic, and also the testing of release. And so the release tests themselves, they can have several purposes and different levels of complexity, because we can either, first of all, try to understand in mechanistic studies, try to understand why and how nanomaterial is released. We can perform model studies or real-world studies where we then understand better why it's released and how under specific environmental conditions and so on. And then we can use these data for example, regulatory assessments, such as exposure assessment, but we can also use it as input for life cycle assessment and safe by design, or safe and sustainable by design. But of course, for using these data, actually standardization and harmonization is crucial, because it enables comparability of the release test results. So for us, it is very important to have standardized release tests so that we can compare the different outcomes and see how this can be used then for regulatory assessments. And release tests themselves, they are basically describing experimental procedures, how to qualitatively and quantitatively assess the potential release of nanomaterials. Sometimes you have to do several steps. So for example, if you want to look at weathering and how a release is happening, it needs to have a combination of UV light and water, because that's what usually is happening at the outside. And then you also have different experimental conditions, but also characterization of the released fragments. But up to now, there's no guidance on how to do that. And this is where our project basically comes into play. So we basically started in Nano. It's a bit long time ago already, feels like that. But we started there, and we aimed to have a project that provides basically an overview of the different aspects of release testing, and to guide the reader on how to choose the suitable release test, and how this can be used for regulatory assessments. I see a yellow thing on my screen, which I don't know if you see. It's not on purpose there. I don't know what happened. Anyways, so we basically started with extensive literature research, established a database with all the different release tests, and developed a decision support system. Of course, we aligned that with different other reports that are out there, for example, from the ECHA and ISO. And then what we basically did is develop a guidance that informs the reader on the state of the art, and that provides basically a decision system where one can choose the suitable release test. And we also implement that in a decision support tool that can be then downloaded and used by everybody who is interested. And for doing this, first we looked at what are standardized release tests that are already available. So you can see here for powder, for liquid, and then embedded in solid matrix. These are all the ones that we found, grouped among the different processes that they are basically describing. So this is more for your reference after the talk, so you can always go back to the slides and look at the different standards. Of course, in our guidance, they will be more described with also the title and so on, but I for first reference, the number is good for you. But as you can see, we also still found processes for which no standard is available yet. And for this, we basically, for now, can only provide literature references. But this is also good, because in the literature, there are already some methods that are quite well developed. They are also used in multiple references, but they are not yet standardized. And basically, what you need to do in addition to the process description of the release test is to characterize the fragments that are released. As I said, they can have different morphology and chemical composition, and also might be transformed and a bit changed from how they looked in the beginning. So you need to appropriately choose the characterization methods. And in the guidance, we will inform about frequently used methods, but also many of them are not yet standardized. And this is the first glimpse of the tool that will be available hopefully early next year. So basically one can choose the input considerations. So if you, for example, would like to learn about what release tests can be done in different life cycle steps, then you can sort all these information towards this point. Or you want to learn which release test is, for example, useful for cutting, then you can also sort the tool against cutting and then be informed at the output window, basically about the standards that we found and that we provide, or in addition on the papers that we found to do methods that provide information on how to do release tests for cutting. And I just brought one example. So the release of carbon nanotubes, as you can see here from Hirt et al., it depends on a couple of mechanical stress, but also the UV light and so on, that from a complex or from a composite material, the nanomaterials are released. So many different things can happen with a composite with carbon nanotubes. what we tested here is, for example, so we have many test cases in the description of the tool, but for example, for abrasion of CNT containing composites, there's no standard that is tailored to nano products, but it provides basically harmonized protocols that can be used. And then in the literature, we also have multiple examples of nano products so that everybody can read basically more about that and learn how this was applied in scientific publications. Yeah, and with this, I would like to briefly summarize. So sum up, because release tests are crucial for understanding and quantifying potential release of nanomaterials. They can have different levels of complexity and purposes, of course. And some processes we identified that standardized and harmonized release tests are available, but for some of them are not. And then it might be needed for some of the advanced materials that the release tests are adapted. So that also depends, of course, on the nature of the advanced materials. And we think that standardization and harmonization of characterization methods is needed, but also of additional release tests so that these data can be used for regulatory assessments. And we are writing currently the OECD WPMN guidance that will also include the decision support system. And here on the right side, you can also see all the partners that are involved and that are doing a great job in compiling all this information and trying to provide a concise and informative guidance in the end. Thank you for your attention, and if there are questions, I'm happy.
Thank you very much, Anna, for a very nice presentation. I think we have time for a couple of questions, and I already see one from your on the chat. And the question is, thank you for the nice talk. What is with the mining as first phase in the LCA? I'm not sure I understand the question. Maybe I can give you the floor. You can.
Yes, thank you very much. Yes, now you can hear me, I hope. Yeah. Because thank you very much for the nice talk, Anna. And the question is relatively because in the first phase of the life of such a material is always the mining. Also you must always begin with some raw material. You must always mine with the raw material before, and their release of materials, of nanomaterials, plays an important role usually. What is about with the consideration of this phase, also of this very first phase in the life cycle assessment? Are there any approaches?
Yeah, thanks, Jörg, for the question. Okay, one thing I realized that I did not mention. So for the guidance that we are writing, we basically do not look at the first step of, so for example, the synthesis of nanomaterials. So I think it is an important step within the nanomaterial, as you say, so that we have the nanomaterial at hand, but we are not looking at the release that is, so we basically start with the nanomaterial. So once the nanomaterial is there, we look at the release. I think, so from mining, as you say, I think during the synthesis of nanomaterials, we also have a lot of bottom-up synthesis, basically, or processes. So you basically do start with chemicals and then you end up with nanomaterials. And then we look at the release of these. We did not look into if you, for example, start with a large bulk material, but I think that will be covered when we look at the milling and shredding and so on. So then I think you could also refer to these release standards, basically, or processes when you do mining. Because I understand mining as that you start with a larger bulk material and then you drop, like you top down, basically, right? That you,
at the begin, at the first begin, you must get your titania. You must get, if you are thinking about all these quantum dots, for example, you must got some materials, some cadmium materials, and so on.
Yeah, I think it would be then maybe a combination of other top-down processes. Yeah.
Okay, thank you very much.
Thank you. We have time for a quick question on the chat from Dan Hodoroaba from BAM, asking about synergies to ISO activities.
Yeah, thanks for the question, Dan. So we contacted ISO, because they wrote this ISO TR 22293, I think it is, for the composite materials, and I got in touch with them on this one to basically also inform that we are writing the guidance. But we are not, so I think the link comes for ISO then also when it comes to developing of new release tests. So in our project, we are not the ones who are developing new ones up to now. We are compiling the information and it will be published via the OECD. But I think it is very crucial to link to ISO when somebody starts with developing and standardizing additional release tests, because then one needs to align and see that not everybody is doing similar things, basically.
I'm happy. Thank you.
Thank you, Anna. So I think we will move on now and get back in the discussion, because I also had some questions for you as well. So the next speaker is Stephen Hodge, who is the Chief Technology Officer at Versarien. So Stephen, now the floor is yours.
Good morning. Hopefully you can see the presentation.
Yes.
Good, good. Yeah, thank you.
It's loading now. It was there. Yeah, perfect. Now it's perfect.
Thank you, Anna, for setting the scene. It's very interesting presentations. I think there's a lot we can also learn from your presentation. Today, I'm going to talk about Versarien, our role in the eye care project. So we're one of the graphene manufacturers in the project, and we're looking at two case studies. One which is looking at graphene in cementitious and concrete materials, and the other is looking at rubber composites for potential use in electric vehicle tires. So as a company, just to give you a brief introduction, we're made up of 5 advanced materials businesses. In the UK, we have a manufacturing sites, and we have 2 companies which were spin-outs from universities of Manchester and Cambridge. So in the UK, we manufacture graphene and 2D material powders, and we also make dispersions as well as some graphene oxide dispersions as well. In a company in Spain that we acquired, we're working on hybrid nanomaterials. So we're combining graphenes and carbon materials with metal and metal oxide nanoparticles. So that also raises some interesting questions about combinations of different materials and how they might have synergistic toxicological response. And then we also have a business in South Korea, which we established in 2021, which is looking at chemical vapor deposition graphene. So not something that we're looking into in terms of the nanotox side. So these are our locations, and we're based within the GEEK in Manchester and the Cambridge Graphene Centre in Cambridge. And as part of the eye care program, my colleague John Benson, who's also on this meeting, he's based at NIBEC, which is a research centre at University of Ulster, and he's performing a lot of our characterization work. So in the eye care project, we're supplying both graphene powders and also graphene water-based dispersions for the use of our case studies. Now, as we're manufacturing more than 1 ton per year of graphene, we have the necessity to be REACH registered in the EU and UK. And so we're working alongside other graphene companies. So we have around 10 or 11 companies now, part of what we call the Graphene REACH Registration Consortium. And we're working together to ensure that we've done the right tox testing and physical and chemical characterization of our materials, providing that to the European Chemicals Agency. I also sit, and Jörg, who's just asked the previous question, is leading the ECHA REACH committee within the graphene flagship. And so we're trying to initiate dialogue and keep a flow of information and advice from all of these parties that we can provide to ECHA through the relevant expert groups or the EU ON Observatory for Nanomaterials, such that we can align ourselves in terms of any changes to regulation. So with EU REACH, we have once you go to different tonnages, you need to provide different information and do lots of testing. So for the low tonnages, it's quite simple and not very expensive. But once you start to go beyond 10 tons per year, then you need to do lots of animal testing. And we try to work together as a group of companies and testing one material that represents everybody. And a lot of these tests will also involve neuro nanotoxicology, which is a focus of the eye care program. And as you can see, when you get to more than 1,000 tons per year, you need to do much longer term testing. And also one of the requirements for the 10 to 100 ton per year is providing what's called a chemical safety report. So this is gathering information from all of the manufacturers of graphene, understanding which applications you're going to be putting graphene into, and then offering advice and providing information about the exposure of graphene in those applications. And most of this is done at the moment as a best guess based on sort of worst case scenarios of exposure. And so the more information we can gather and more accurate data, we could then feed into these reports and provide more up-to-date information. So as you can see, there's lots of applications where companies are selling graphene into, for example, adhesives, textiles, polymer composites, construction. And so each of those will have very different life cycles and complex pathways for the nanotox testing. So within eye care, as I mentioned, we've got 2 case studies. The first is looking at one of our products that we manufacture. So we have an activity which is 3D construction. So we're developing concrete mixes containing graphene, and we incorporate the graphene through a water-based mixture. So that's a dispersion of graphene and some surfactants or some polymers. We actually take the customer from everywhere from the design of a product to the delivery. So the third picture here, what you can see is our robotic printer, and that's extruding at around 2 tons per hour a concrete mix, and that mix can contain graphene. So we manufacture this dispersion in our factory, and then we also then take it through to printing final products. So we're adding graphene to concrete to improve sustainability. We're looking at improving the compressive strength and flexural properties of concrete, and also looking at improving the early strength. So if we can cure concrete faster, we can build faster, and also making more durable structures that has an overall impact on the CO2. So we're putting this into a number of different applications, and we will be doing the first house building in the UK using a robotic 3D printing system that won't contain graphene, because we're trying to work with a very risk-averse industry, and we're trying to push materials and the new technology. So in some cases, we're not using graphene in these applications. So this is a kind of cross-section of 3D printed mortar material. You can see through the life cycle, we will have around 6 or 7 different types of material or blends. So we have the graphite raw material, we have our surfactants, that we then have that as a blend in water. And then we have the cementitious materials where we're just using cement and some fine aggregates of around 3 to 4 millimeter. We also have to use a retarder. So when we're 3D printing, it actually cures very quickly within around 5 minutes. And so we add a retarder to slow down that printing process. And then so we have a wet mix, which is coming out of the nozzle. And then when it's dried and cured, for example, in use with concrete, and obviously historically we've had issues with asbestos in concrete, people will be likely drilling, sanding, abrading that concrete, or crushing it at end of life. And so there's a number of different mechanisms or ways in which somebody could be exposed to the nanomaterials. But just to insight into some of the results, we're achieving much faster early strength, improvements in water permeability. And so what we've done in eye care is try to identify and prioritize which are the most important samples to collect. And so what we'll be doing is collecting sanded concrete as a kind of first priority, which hopefully will deliver kind of particle sizes which are sub 10 microns, which is needed for the program. We've also done a lot of testing already on the graphene in the water-based dispersion. That's this material 3. That's already here. So we've already had some results on that material through the program. In terms of use case 4, we're looking at EV tires. So again, one of the challenges with EV vehicles is that tire abrasion is likely to be much higher because batteries are very heavy. You also have much higher torque when you're using an electric motor, and that causes more abrasion of the tires. And actually, there could be more emissions from the tire from the tire abrasion than actually from exhaust emissions. So again, we see various benefits adding graphene into rubbers. We see improvements in mechanical properties and abrasion resistance, and hopefully that will lead to, again, more sustainable, longer lasting products. And when we manufacture, it's again a different route. So we take a graphene powder that's blended with lots of other additives and rubber materials in a Banbury mixer. It then goes through 2 roll mills, and we produce these sheets of uncured rubber. And then that uncured rubber then gets put into a mold and cured to make a final product. So again, these materials are very complex. You've also got potentially other nanomaterials. So nanosilica is used a lot in tires, and carbon black. So we've actually tried to simplify some of these mixtures so we can just identify the graphene component of these. And again, understanding where is the most likely end of life or usage situation for the exposure, and that will be in the usage of the tire when the car is being driven. And so we're going to try and mimic that by looking at some abrasion testing of the rubber compounds. So key challenges for sample collection is for eye care, we're only interested in the respirable fraction, so particles less than 10 microns. And we also want to collect several grams of material. And that shouldn't be a problem, but yeah, we've had to reach out to institutes like the HSE in the UK to get some advice on how to collect these samples. We also don't want to expose employees to dust during the sample collection. We've seen in the literature a number of papers where people have put some homemade devices together to sort of have a way to collect on a filter. And with concrete, yes, you can get very small particle size, and so that's going to be very useful. On the side of rubber, there's some papers out there looking at abrasion testing. It seems to be that the particle size, the kind of agglomerates that come off of rubber, seem to be tens to hundreds of microns. So maybe there aren't particles that we're going to collect that are respirable, but we'll have to investigate and try to see what we can achieve. So HSE have pointed us in the direction of these MDHS 14/3 and 14/4, and these documents suggest you should use an IOM air sampler, so Institute of Occupational Medicine. This is something that could be worn by an employee to monitor exposure. We're going to be using PTFE filters on there, which are 1 micron in size, to collect all of the necessary particles. And we're going to be placing those inside a closed cabinet such that we can use this filter system as the extraction point, and hopefully be able to collect several grams of sample at a time. So that's the plan for the next month, and hopefully we'll be in a position to be providing collected dust to the eye care partners early next year. So we haven't quite got everything in place yet. We're waiting for a few of the filter capsules to arrive before we can start doing the measurements. But at this point, once we collect those samples, we'll do some in-house testing, particle size analysis. We'll be doing some microscopy before sending those out to eye care partners. So I think we've learned a lot from Anna's talk potentially, and hopefully we can read some of those other ISO standards that have been pointed out for things like sanding and of solid materials. But any further input at this point from anyone in the audience, that will be hugely beneficial before we start our trials next month. So with that, thank you very much. And again, thank you, John, our senior scientist, for his input into the program and leading most of the work from Versarien's side. So again, happy to answer questions now or later in the discussion. Thank you, Blanca.
Thank you very much, Stephen. Do we have any questions? I don't see anything on the chat, but maybe people online. Otherwise, I like to start with one question. Maybe I missed it, but what is the concentration of graphene in the concrete and tires that you have presented?
Yeah, so usually it's in the concrete, it's about 0.03 weight %. So we're talking very small amounts. So one of the challenges we might face is actually, will we see any graphene within the samples that we collect? That's obviously a good thing if we don't see any graphene, but also we might like to try and increase that dosage so that we can actually, we can actually see something. Yeah, that's an open question that we've discussed at many eye care meetings. In the tires, again, it's quite a small concentration, slightly higher than we put in concrete. So you're talking something around 0.1 to 0.5 weight%. But I think maybe in the concrete sample, we might have more chance of finding carbonaceous material through things like SEM and EDX and other characterization tools. In the rubber tires, obviously everything's carbon based, so it might be more challenging to get discrete characterizations.
You said 0.03, sorry, 0.03, yes. Right, percent. Yes. Okay, yes. So it's really, maybe, yeah, it's so tiny.
Roughly
because
you end up with about 1 kilo of graphene in 2.5 tons of concrete. So it's, yeah.
Because I know some people will then concentrate it to get into the respirable fiber, but sorry, this is graphene. But I wonder if this is also representative to the real situation, because you are also concentrated to get into what you want to see. So it may not be representative. But I see a question. Yeah, we have some questions in the chat. So from Dan, excellent talk. Do you control the distribution of graphene in products? Yeah.
Yeah, it's a good question. So this is the reason why with construction we provide a water-based dispersion, because one of the challenges when you add a powder, it's quite a hard way to mix graphene and get a good uniform dispersion. So we believe by putting it in water first, we're enabling us to get a better uniformity. Yeah, the control of distribution is done by, with rubber, for example, in the compounding, the mixing process has to be long enough to enable you to get good mixing and blending. So yeah, there's no guarantee. Of course, there will probably still be some agglomerations of graphene, and perhaps when the concrete is curing, you will get some agglomeration of the material as well.
There is another, seems like Dan was happy with the answer. There is a question from Asmus in the chat. What's your estimate of the number of graphene layers in the product you disperse in concrete and rubber?
Yeah, so the graphene powder that we start with usually is around 5 to 10 layers. But yeah, perhaps it can re-agglomerate in the process. Maybe during some of the mixing processes, it gets thinner. Again, understanding these transformations is quite critical. So once we put graphene in a product, it's actually very hard to understand what it has become. So yeah, difficult to say, I think.
Thank you. I don't know, Asmus, if you want to, are you happy with the answer? I don't see Asmus. Yeah, he is. Okay. Now, yeah, I was also wondering about this device that you introduced from IOM. Is that like a filter which captures the particles, and then will you do a TM analysis?
Yeah, so it has like a cassette which has a filter inside, and then once you've collected the sample, you can then seal that cassette, and that can then be sent straight off to a lab for testing, so avoiding any sort of contamination issues. So it seems to be quite a nice product that allows for this kind of testing. As I say, we're waiting for some of the components to arrive, so we haven't actually fully tested it, but it seems like it's widely used. We do use this in another part of our business as well, which is dealing with tungsten carbide and milling powders. So we do have some of this capability in the company already, and it's used by some of our health and safety officers that we have in the company.
It's very interesting. I look forward to the results, see how well you manage. And also, Stephen, he said anybody who is keen to give some advice, I think he said that he will be open to any kind of suggestions as well. I mean, these are research projects, of course, and we are learning as the project is moving on. So we are learning. Thank you, Stephen. So if there are no, I don't see any other questions. Okay, so we can move on to the next speaker, which is Pohl, a regulatory expert at Blue Frog Scientific. And I must say that they are also leading the ECA project on sameness. So hello.
Hi. Yeah. Hi, everyone. Right, so I shall try and share my screen. It is not letting me share my screen. Let's try. Give me 2 seconds and I'll be back.
Yeah, sure.
Sorry.
Your chance to ask more questions to Stephen, unless he's already signed off and done for the day.
I'm still here.
Oh, there he is.
Ah,
There he is.
yeah,
Perfect.
okay, because I lost
Okay.
Kai for a
Yeah,
little bit.
no,
Kai's,
I-
Kai's back as well. Kai's back as well. That was fast.
I had to leave. So apologies for that.
It's fine now. We see.
Great. Can you?
Now we see the two slides, the one and the next. So
We can see
could-
your presenter's mode. You need to be on
right,
the other
okay.
screen.
No worries. Stop sharing. I don't know why it's done that.
There was a button, swap
I'm not
screens.
that
Just
technically now.
start again. There's a button, swap
Okay.
Yeah.
screens.
If you go back to what you did exactly just now, Asmus can talk you through. Yes,
Yeah.
there is a swap display top row, third from the left. You can click on there
yeah,
in
there
your
are two
presenter's mode.
parallel arrows to the left of your screen. There
In
are
your
two
presenter's
parallel.
mode, all the way to the left and to the top.
Yeah.
The third one says swap display.
Right, I've got you. Great, thanks.
Voila,
Sorry.
thank you.
Technical difficulties. Right, I'm really not that inept at IT as much as it might look like I am. Like Blanca said, I am a regulatory and scientific consultant with Blue Frog Scientific. I won't be going too much into the science, so probably not going to stretch anyone's grey matter too much. More about the practical applications. I am going to come at it from a nanomaterial or nanoform perspective in the first instance, and then touch a little bit on advanced materials as we go through. That is not helpful at all. Apparently I am that inept at IT, so I don't know why it's doing that. Sorry, to stop sharing again.
If you like, you can send me your presentation and maybe I can share.
Yeah, I don't know.
Either that or you just share it directly from the program you're running without the presentation mode.
Yeah, could also do that.
I think your font size is large enough for that.
Yeah. Now everything's crashed.
I think we lost Kai. He's frozen.
He
on
was
my
just
screen.
saying that he had crashed, right?
Okay.
Let's
Let's maybe, yeah. I wonder if we could have a little discussion with Elizabeth. Do you have Kai is not here anyway. I was wondering if you had his presentation.
No, I don't have, but I just wanted to suggest maybe you can ask some questions to Anna and Steve already.
Exactly.
Start a bit of the discussion until Kai is back.
Yes, because I also had a question for Anna regarding modeling tools, because I think you briefly mentioned them. How far can we use them to anticipate exposure in the occupational setting? I'm not a modeling person at all, so but I heard it from your presentation briefly.
Yeah, I think there was a little tweak in the internet connection for one moment. So which methods do you set for the exposure assessment?
Oh, modeling. I heard from your presentation that the modeling was also available or some, you kind of briefly mentioned it, modeling for exposure.
Yeah, I think many of the exposure models, they actually ask for release. So they want to know at least a number as an input parameter so that one can estimate how much of the chemical or material is actually released. And I think for that, the release data can be useful so that one can actually run more appropriate exposure modeling.
Okay, so it's not that with the FISChem, we could anticipate already. Maybe I'm going too far. I thought maybe if we have some FISChem data, we could already model how much we expect to be released. And
yeah, actually, I'm also thinking, like, for example, also for the matrix, if you have a very brittle one, then it would be higher than if you then have a really tough one. But so up to my knowledge, there's no efforts right now or no publications that is really pinpointing to a FISChem parameter and then saying, okay, if it's like this, then you will have a release of X, Y, Z. So this is that I'm not aware of. But of course, that will be very smart. So then you don't have to run the release tests. But what is usually done, I mean, there are also modelings of release. I think also EMPA is doing a lot on this. So I think they are trying to estimate how much is released, but then you still have several input parameters that they need. So I think it's not on one FISChem parameter mainly, but it's maybe on a combination of those.
Yes, and the other question I had as well was when we look at exposure along the life cycle, and of course we don't have a lot of resources, we have to make priorities for standardization. Sometimes wonder we are focusing on the occupational exposure part, but at the occupational setting, workers will have some protection measurements. We have safety rules in Europe. However, for a customer, I think like the use phase. Sometimes I think it may be more important because, for example, I can think of a baby maybe chewing some. Maybe customers are not so protected, but then exposure is much reduced because we are always thinking that maybe the hotspot will be the end of life of the. So I don't know if you have any thoughts on this. It just occurs to me every time we are looking for hotspots along the life cycle. Where should we focus?
Yeah, I think it's a good question. I mean, I'm coming from the occupational safety side, so I'm also focusing more on this. But that's why I'm glad we have in the project the BFR and UBA, which is in Germany, the Federal Institutes for Environment, UBA, and for the consumers, the BFR. So, and they always also, inform that one needs to take into account the misuse so that the consumer is basically using an item or a product not in a way that one should use. I think there's a lot of things to do and preventing that consumers are getting exposed to nanomaterials. And I think that's why it is indeed crucial to look at the products along the life cycle and to see which uses are foreseen to at least cover this, and then also see what maybe potentially misuse could be. I think that they are more the experts on the different steps that they usually take into account.
Yeah, just now that we are working on this project mapping hotspots along the life cycle, I realized that it's just natural to focus on the occupational exposure, but sometimes, yeah, I do wonder about misuse, like you said. Yeah. Actually, from your mapping of ISO, I didn't see the ISO 10993/22 from the medical device regulation and leaching. I don't know if you consider this. I had a very quick glimpse on your mapping of all these ISO and standards. I don't know if you consider it and you didn't think it was relevant or you didn't.
Yeah, that's a perfect moment, Blanca, because then we can still incorporate it. So we tried to find as many as we can, but if there are some that one spotted that are missing, I'm very happy if you can send me the numbers and then we can see if it matches. Yeah.
Yeah, it was a quick glimpse, because it was only a minute. But
yeah, it's also a lot of information. Yeah.
But that sounds like a great effort that you have done, and I'm looking forward to the documents from the OECD. So I don't know if we can continue with the discussion now. It seems like Kai sent a message that his lab was frozen. So maybe we could start some discussion already. Maybe for Stephen, if you are here, who do you think should be responsible, along the life cycle of doing all this release testing? We have seen from your rich work that you need to anticipate exposure scenarios, but you are only anticipating. Would you do you get some also information from downstream users? How is this whole process put together?
Yeah, it's a good question. I think the primary responsibility should be with the producer of the nanomaterial, but I guess we cannot be experts in every industry. So, for example, when we're supplying graphene into a polymer compounder, someone who's mixing the graphene powder into the polymer, they might already have some experience with exposure monitoring. But also we've done projects in the past where we've worked with polymer compounders to actually do some of this exposure studies, so we can get an idea, and we can also give them confidence that their employees aren't going to be exposed to nanomaterials. So, we find there's like a drive from a lot of industries where the word nano strikes fear into people, and people don't want to use it because they think it must be toxic if it has the word nano in it. So we've got to provide as much information to give them confidence that there aren't any harmful issues. So having that REACH registration and showing so far that graphene doesn't pose any effect is quite good. I think academia also has to play a key role, and some of the early stage testing of nanomaterials toxicology is quite crucial to then helping those that are trying to scale up the technology how to proceed, and also developing new methods for testing nanomaterials is quite key. And some, as like OECD, some of the guidelines aren't suited to nanomaterials, so there's some work that needs to be done there from academic partners as well as the industry.
And what have been your incentives to look into release? Because right now you are a producer of pristine graphene, right? But you are doing all this work, anticipating issues at maybe during use and end of life. What is your main incentive to do this work?
Try to be responsible, and we have a duty of care to our staff that when they're manufacturing these materials, that they're not going to be exposed unknowingly to. I think, was there a question?
Yeah, I think someone is not
Tomaso is
talking. Tomaso is not.
Thank you. Yeah, no, I think, as I said, there's a duty of care to our staff that they're not going to be exposed to anything, and we also need to make sure that we're following all of the necessary regulations to be able to sell these products legally, and to make sure that we're not going to bring any harm in the future. So as any opportunity to do these sort of studies and work collaboratively, and would really help the business.
So it could be seen as a regulatory preparedness as well. You are getting ready for what's to come. So it's that's really nice to hear. Thank you, Stephen. I see now, Kai. Are you ready now? We can.
Yeah, I want to. Well,
I have otherwise more questions on the line.
Yeah,
So
I think so. Sorry.
Let's try.
That I think this ranks up with one of the most embarrassing presentations I've ever given. I'm really glad that it's being recorded.
We
as
still
well.
have time. Go for it. We are really keen to listen to your presentation.
So yeah, so I'm going to be talking more about the practical applications and what's happened with things from a regulatory perspective, and where some of this research ultimately goes. I'm going to talk about a little bit of the progress from a regulatory science point of view. I'm going to assume some quite a lot of base knowledge here actually as I go through, because I don't want to, it's really going to be a quick skip through just to emphasize some of the issues that we can have, but also are they unavoidable. So I will talk about some of the definitions and the dissolution, and a little bit on exposure assessment as well towards the end. Progress in the last sort of decade or more, and from a regulatory science point of view, I guess really last 6 years, driven mainly from EFSA and ECHA's side. We have a definition for nanomaterials from 2011, which meant that we knew what we were going to regulate, which is great. So then off the back of that, there was some work on to sort of the regulatory preparedness of nano materials. And then this was updated in 2022. So of course, everyone uses the same definition. At least in theory, I think that's what's supposed to happen. And later on, I'll go into a little bit more on the definition side of the things. From a regulatory perspective, again, we've got new concepts that have been brought in, like sets of similar nanoforms under REACH to try and ease compliance. We've had lots of new guidance documents and test guidelines that people have outlined in the last couple of days from the OECD. There are still some caveats with some of these. For example, we've got the OECD test guideline 125 for particle size and size distribution. But when we want to validate the method we're using for our nanomaterial, say that we're using a platelet, for instance, there aren't any standard reference materials for that. So that can become difficult also. We have the OECD test guideline 318, but that's great, and we can get the dispersion stability from that. But from a regulatory perspective, what this also tells us is what is the environmental compartment of concern. If we have a nanomaterial that sediments, then it would make sense to test that in the sediment. Unfortunately, this doesn't line up with the regulatory needs and requirements, because then we wouldn't be able to classify or not in line with the aquatic system. So although we would get this information, we know that sediment is the most relevant, we still might end up having to do an aquatic test. The OECD applicability of the OECD test guideline 442D for the skin sensitization. Obviously, people have been talking about animal replacements and things, which is great. It's one of the things that my team does as well. But again, this is a great first step, but this only covers one event across the whole adverse outcome pathway. So actually on its own, is it as useful as we need it to be? And are we ready for it to use it for regulatory purposes from nano? Again, probably not just now. There are other things that can be done as well other than in vivo testing, but most likely a lot of the time the difficulties in the testing and the in vitro methods will lead to some sort of in vivo test. So although these things are in place, we've still got some way to go. So that's just to illustrate some things there. And then on top of that, can we find labs? Finding a lab that will deal with nano and nano-specific tests can be difficult. Particle size distribution is a good example. Again, the microscopes are not cheap. The contract research organizations will not necessarily outlay that kind of money to run the number of tests that they need to right now. Also finding labs with the right expertise that have done the risk assessment internally to be able to perform these tests. I've had contact with labs that have told me that they will do gene tox, but they can't do skin sensitization because they haven't done the risk assessment within the lab, and that's the end of it. So that's some of the issues in and around there as well. So of course, on top of the regulation and some of the advances in the regulation and our scientific knowledge, there have been lots of guidance documents and regulatory guidance documents addressing nanomaterials. So we've had some from EFSA on the risk assessment of nanotechnology in food and feed. We've had a couple from there. We've had some about establishing the presence of small particles. We've had about how to create substance identification information from ECHA for regulatory compliance purposes. We've also got the appendixes about the data requirements, which will tell you, specific caveats and pitfalls that you might find when you're trying to do standard testing to fulfill the data requirements for a nanoform under REACH. We've had the identification of nanomaterials through measurements from the JRC, which is really helpful when you are trying to decide what kind of things you should do to decide whether you've got a nanomaterial or not, and how to go around the testing. And then we also have, which is really helpful, but it is an odd one for me. We also have guidance on the implementation of the new definition, which is a strange one for me because I feel like a definition should be a closed unit. But it is complicated, and absolutely we do need this document, but just shows the complexity in behind defining something like, an advanced material or nanomaterials. That not only do we need the definition, we need a guidance to explain the definition. None of the regulations specifically address advanced materials at the moment, which people will be aware of. So talking about definitions, at the moment for the nanomaterial definition, I mentioned that we do have one for the EU that has been updated. But at the moment, where there is a lack of coherence between the new EU recommended definition and the current regulations. So, for instance, REACH is still very much using the old one, although I believe it's going to be updated. There's even a lack of coherence between EU regulations. So, REACH uses the EU recommendation from 2011, and then the cosmetics regulation uses another one, which I've written there, which talks about it being insoluble and biopersistent. There's also a lack of coherence between countries and jurisdictions. So basically what you end up with is that your nanomaterial can both be a nanomaterial in one jurisdiction or regulation and not a nanomaterial in another. When you're trying to communicate about your nanomaterial, it might look like a lack of transparency to your downstream user. It's actually just a multi-dimensional space that your nanomaterial lives in. And also in worst case scenarios, what you can end up with is having to create sets of different data for different regulations, which obviously increases the intensiveness of not only testing, but potentially animal testing as well. So like I said, there is this multi-dimensional space as far as a nanomaterial definition. The only word of warning that I would say is that I can see it starting to happen a little bit with the advanced materials. Don't do it, please. It does create a little bit of a mess, and the main thing is that everyone talks, which I think we are much better at doing now. Already the definition of an advanced material and nanomaterials and definitions of some advanced materials coming through is creating interesting conversations, where, if you've got a nanomaterial which is composed of a mixture, which is, say, an advanced material like a nanoalloy, is it a mixture? Is it a material? Do you register it as a whole substance? Do you register it as a nanoform, as a whole substance? Do you register each substance separately? And if you're registering each substance separately, can you use the data set from one of the nanoforms or both of the nanoforms? And then if you can do that, how do you even prove that it's within a set and that that data is relevant once it's in an alloy, for instance? So defining things and how you define them can have wide implications onto the test that you need to run, as well as how you even test a material and how you view it. So that's just a very quick whiz through some of the definition stuff. Another interesting part is, we come up with the regulations, they're put into place, different data requirements come up, and then you must fulfill them. It's your legal obligation, say as a company that produces nanomaterials or imports them, that you must fulfill these data requirements. So one of the data requirements under REACH and a lot of other regulations as well that have addressed nanomaterials is dissolution, which is good. And it makes total sense because then you know whether you are, if it dissolves fast, then you're really talking about testing the ion because that's what's going to drive the toxicity. If it dissolves slow, then you've got potential that the nanoform might drive some toxicity and there might be something nano-specific. If it's within a medium time frame, maybe you have to test both, or the worst case. At the moment, though, we currently have no test guideline or guidance document, and from what I've heard in the last couple of days, it's very much looking like 2025 or 2026. So without any expertise for, say, an SME or something, this can be a real problem because they want to register their material, but they don't necessarily understand how to go about the tests, nor can they find readily available CROs that can do them, and also understand what they need from a regulatory perspective. So it can slow things down significantly. And this is despite the regulation being in place since 2020 and 2018. Now, I'm not saying that it's anyone's fault. It isn't. It's a complicated subject. It's a complicated test. It's just where we're at, but it does cause difficulties. So, defining also fast, slow, and medium is also difficult. And something that is, again, somewhat of a multi-dimensional space. There's some instances there of what people would consider slow dissolution from the Gracious project, which is about read across and grouping. But you can see that actually slow needs to be brought into context also of where it is dissolving, which again adds layers of complexity to the interpretation, and then also your testing program of what am I going to test? So it could be slow in one medium, but fast in another medium. And then you need some that are nano-specific tests and some that aren't nano-specific tests. And then just to touch on, don't confuse, speed with completeness. And again, this is where we start to fall into somewhat of a multi-dimensional space. So here's some stuff from 2015 from the OECD talking about dissolution, high, moderate, and low. And you can see some percentages there. And then this is very much for environmental fate. And then from 2022, from one of the guidance documents in ECHA, you can see that actually what they're saying is that it needs to be highly soluble, so over 33.3 grams per liter and under 10 minutes. So again, the way that you do something might change practically between the environment and humans, and depending on what regulatory framework you're within. EFSA and ECHA use the same as I've presented here. So that's just very briefly, touching on, it's difficult to place the test. It's difficult to understand exactly what you need to do for the test for, regulatory longevity of your testing, which is expensive. And sometimes interpreting it, feeding it into your integrated testing strategy is also difficult. This isn't limited only to this particular test. Then, just to touch very quickly on the exposure side of things, the OECD have compiled a list of varying tools for nanomaterials, and that covers the environment, but there still isn't a regulatory consensus on which one should be used, unlike conventional or non-nanoform chemicals, where things like EUCIS and ECHA TRA and CHESAR have been entrenched in regulatory use. Some of the tools that come through are good, but don't fully account for things yet. So SimpleBox for Nano doesn't account for exposure at the local level, but it does at the regional level. And from groundwater models for plant protection, for instance, haven't necessarily been updated to account from this, and they are very difficult to validate because of the background. Normal background of something, say, like silicon. Talking about going with worst case that we just heard about when you're doing an exposure assessment, a lot of industries or specific bodies within industries will come up with specific use descriptors and also specific release categories and determinants, where as an industry we know certain things are going to happen from a risk management measure. We know certain things are or aren't possible because of the materials that we're working with, and that is a way to increase realism and to not restrict the market as much. These kind of tools and terminologies and things would also need to be for advanced materials as they come into the regulations, if they come into the regulations. So we are lacking in some areas, and I might sound a little bit negative by some of the things that I brought up. I'm actually not. I'm actually very pleased that the regulations are in place, because it does create a fair and accessible market. Without the regulations, what you end up with is people are afraid to try and go into the market due to uncertainty. And then you end up with strained innovation, restricted growth, people go into market and manufacture elsewhere. The regulations being in place also highlighted lots of good research, but unfortunately that couldn't be used for regulatory purposes. But it did create an acute awareness of the regulatory science knowledge gaps, which increased regulatory relevant data, which then feeds back into the regulatory science and then ultimately leads to less uncertainty. Not only that, it drives the demands from industry, which drives the demands for the testing to the CROs, and then the CROs then increase their capabilities. So actually, without the regulations being in place, these things don't happen, or they don't happen fast. Should we directly regulate AdMas? This is my last slide, just because I really am rattling through things quickly. Well, I'm not sure. Nano could fall within existing categories because that's one argument that's been raised in the last couple of days. Well, an advanced material could be a nanoform, could be a polymer, could be another substance. But the difference with nano is that it changed the paradigm for regulations, where you weren't testing on solutions anymore, you were testing on a material. So now we have that, and that's chemical-based regulations I'm talking about. However, what we will need for advanced materials is we will need to know what an advanced material is, so that we know that it might be tricky to test or take through a regulatory program. We will need tools, we will need tests, we will need foresight and forethought on how to do with them. But do we need to put them directly into legislation? I'm not sure, because you are then trying to ultimately regulate something that is transient, that could be advanced now, that isn't advanced later. So I think that becomes quite difficult. And with that, I thank you for everyone's patience as I went through my IT issues. And if you've got any questions, I'd be happy to take them.
Thank you very much, Kai, for this very nice presentation. I see a question on the chat from Susana Loureiro. Sorry if I'm not pronouncing properly your surname. Regarding materials that are composed by several nanoparticles or nanomaterials, there are already a few papers using the prediction modeling for mixtures. What do you think about this? Is this the way forward? How are formulations with one nano component being dealt with?
Sorry to read that because you said that quite quickly.
Yeah, so it's about prediction modeling for mixtures.
Papers using prediction.
And we have Susanna here anyway. Susanna, if you want to highlight your question yourself.
Yeah, please.
Hi. Good morning. Hi, Kai. Nice to see you. So I was thinking about the way that the mixtures are dealt under the regulation nowadays for formulations, using some prediction model, using the additivity modeling that was used previously for pharmaceuticals. I was wondering, because I have already tried it, and there are also not many papers using these prediction models like concentration addition or independent action to try to predict the hazard of certain mixtures using these same models. And I was wondering if this is the way forward, and if not just nanomaterials that are composed by several particles or materials nano. If there is a formulation with one component that is nano, how is the regulation dealing with this?
Yeah. So from a mixtures perspective, very much from from a reach or plant protection perspective, you would almost deal with them each separately, and then if you're dealing with a formulation, you can have specific tests on the formulation. As far as predicting the estimates from an exposure point of view, that's not something that I would do in the regulations that I work in. And when you're talking about one nano component being dealt with, so that basically will go through normal risk assessment processes. So whether you've got monitoring in place and have direct measures, which is unusual, or you are trying to predict it with some of the tools that do exist, because like you say, there are some out there. That the only problem with that is, yes, you can go and use them, but because you're not sure how they're going to be viewed by the regulators, and it's not like something like CESA, you're almost immediately taking a risk, and then the onus is on you always, of course, to prove that it's scientifically valued and justified, etc. So it just places the onus a little bit more on the person that's registering it.
Thanks.
Thank you. I think Susanna is happy with the answer. I see another question from Elizabeth Hunish on the chat. She says, you said regulation drives regulatory research. Do we need to place regulation first as a driver for regulatory research?
I think we need to know what we're talking about first. I mean, obviously, from a nano perspective, what we started with is there was this real big uptake in nano research over the last 2 or 3 decades or more. Then people started to understand the technology and the advances that it could make to people's lives, etc. And then at some point we get to this critical load, I guess, where regulating something like that has to be done to avoid, unwanted effects and for protection of humans in the environment and things like that. So I guess the argument there is then, well, maybe we should have it for advanced materials. Things aren't always necessarily, written within the legislations to drive the research. For instance, there's lots of UVCBs out there that people use now. They are very difficult to test. They have lots of their own problems, like nano, like advanced materials. People are working on that because they have to register it. So I think sometimes it's a combination of two things, whether it's written into the legislation. Now, nano needed to be because it became materials based, so it was a suspension you were testing, not a solution, which totally changed the paradigm. Advanced materials now come in, well, materials are kind of regulated with the way that nano is set up. Do we need to extend that and say that any advanced material should be tested as a material? I don't know. But the other side of things, other than just, it being in the legislation, is actually just uptake in use. So the more of it that's out there on the market, the more people will need to register under REACH, for example, or register under EFSA, under the plant protection products. And then they'll have to start solving these problems. So then there's that immediate interest.
I guess my question was not so much into the direction of what to do with advanced materials. I think it was more a general one. I think it's always a chicken and egg problem. You say it's not wise to place some legislation if you don't have the test methods in place. Put it like that. It's making it more difficult for industry to fulfill their information requirement. I don't say they can't, but it's more difficult in the end. And it might lead also to multiple testing and all the unwanted effects we don't want to have. On the other hand, if the legislation is not in place, people might not be interested to develop the test methods or to go through an evaluation process and to go through an harmonization and standardization process because they don't see the need. And then having the legislation in place is in the end putting pressure on everyone, as you said, on the member states, but also on the industry to become active and to support the development. So I think it's a difficult one, and I wanted to hear your view because we're coming from different ends in the end. You're coming from more of the industry side, whereas I'm having the member state view, and I just wanted to hear your answer. But I think we're coming in the end from the same side. We're seeing problem either way. So there's possibly not the perfect solution in the end.
Yeah, no, I totally agree with everything you just said, and I think it's important to state and realize that actually it makes it difficult for everyone, not just one side. It's difficult for industry, it's difficult for the regulators. Everyone's having a headache with it, and we're all just trying our best.
How about having both working together? I mean, I know this could maybe not so easy, but thinking about safe and sustainable by design, if we want to have I don't know, regulators engage early in innovation settings, maybe together we can work towards getting something ready on the market when time is there. I don't know if we can merge both worlds and help each other a little bit from the beginning. Just came to mind when I listened to you both. Maybe the solution could be.
It is happening. So it's not that the world are divided. So we're talking to each other. So we're trying to find solutions together in the end. I think it is happening. But there are always also the hurdles. So with safe and sustainable by design, it's a well-intended thing. So that's where we start from. And then it's very difficult, I guess, on the sustainability side. So there are a lot more things unclear than on the side of how to test for safety. So I think a lot of the things still need to be defined and need to be doable for industry in the end. And then the question is like, what do the regulators do with the information, or where does the information even end up? I guess it stays with the industry. So it's well in their capacity to do it or not. And so I think there are a lot of unanswered questions there.
I think it happens more now than it ever has. With nano, outside of nano, there's much more of an open dialogue and working together between industry and the regulators. Could it happen more again? Yes, but we're certainly seeing advances in that direction.
I have a quick question for Kai as well. I think that the cosmetic regulation is going to be updated maybe next year. Do you anticipate issues for nano now? Perhaps they take the definition now.
Yeah, so I think they are going to align the definition with the EU one. So far as issues with the regulation, it's not a regulation that I'm all that familiar with. It's not one that I work in much. So I can't comment whether it's going to cause issues or not.
We'll keep our, get to following this. I'd like to have all the speakers now. If you can take and turn your camera on now, because we still have 10 minutes, a little bit less than 10 minutes for the round table. Thank you. Any questions from the audience to any of the speakers? I don't see anything that was left behind on the chat that I didn't see, perhaps.
I think there's one in the chat from Eric towards Stephen.
Okay. Eric, please take the floor, Eric, because I don't find it now.
Oh, I think I have answered it directly, but Eric's question was about, it says, actually, I've lost it, Eric. Oh, it says, what challenges will you encounter when characterizing released particles from tires and concrete? So my response to Eric was, we haven't yet encountered the challenges because we're due to collect the dusts next month, and I would anticipate that the typical graphene characterization, like Raman, is probably going to be obscured by all of the other components in the mixture. Will we find free graphene particles that are loose from the other materials? I don't know. So that's something we'll come across, and we'll obviously try to use a mixture of different microscopy techniques, maybe some XPS or other elemental analysis to try to see what we can find. But I'm sure those challenges will be coming in the next few months.
Yeah, thanks. And I also had a question for Kai, which I see now that I put that forward to Stephen as well. Sorry about that, but that was for something that went wrong in the chat there. But Kai, do you think advanced materials would fit in chemical legislation, or do we need something else? I mean, we've seen the issues with nano, which is sometimes a challenge to put that into chemical legislation. But
yeah. I mean, I'm not sure. I think we see how it develops, and I know that's me sitting on the fence. I mean, you know, when you think of advanced polymers, will they fit into polymer reach, for instance? Perhaps they do. If you decide that it's not got polymer properties, but it's got nano properties, then it falls within the nano side of the legislation. If you decide that it's got neither of those properties, then perhaps it just falls into the substance legislation. So it's really going to depend on the advanced materials and actually the properties that you have tried to gain from it that make it that advanced material to where you end up with. So I think it's that initial categorization that's going to be important. If we start finding that the advanced materials don't fall into any of these apparatus that they've got from a legislative perspective, or the ones they're bringing in with polymer reach, for instance, then we need something additional.
Okay, thanks. It's complicated, that's clear.
Yeah, thank you, Kai. I see also a question from Elise. Elise, would you like to take the floor? I think it's more a general one.
Yeah,
Elise?
it's more like about like the willingness of industrial to maybe work on aspects that are not mandatory regulation-wise. Maybe it's coming back from the previous discussion and questions with Elizabeth regarding the eggs and chicken problem, I suppose. And I was just wondering if we really need more like public-private initiatives. Was in a Safe by Design conference last week, and it seems like there are some initiatives that really help innovations when it's kind of mixture.
Thank you, Elise. Any comments on these public-private partnerships to anticipate non-regulatory issues, which are, like Steve said, important to address anyway, because we want to be responsible.
Yeah, I mean, I think there is more. You know, it's not industry. I think at some points in the very distant past it was a them against us thing, whereas now, you know, industry want to be responsible. They want to be ahead of things. They want to understand their materials and the risks and the exposure, as well as the efficacy. And I think we are seeing more of these kind of projects coming through. You're seeing more industry also taking part in wider EU projects as well. So Anna, I think you had something to say also.
Yeah, I think I fully agree. I think it is absolutely needed. It also brings a lot of side benefits. I mean, when we speak about advanced materials and the foresights on what is going on, what is the new development. So I think by having those projects is a good way of keeping the different stakeholders also informed about upcoming things without maybe like telling the secrets, but just to keep people in a loop and so on. I think funding is very crucial for all of those participants. And when we speak about standardization and harmonization, I think especially then we need long-term funding, and we cannot just with a 3 years project and stop with all the development and not continue because we do not have funding or because the people have to switch their jobs. So I think it is absolutely needed, but a long-term perspective for the different stakeholders would be essential as well as coordination and also setting of priorities, of course, on the developments and so on.
Yeah.
Thank you.
If I can just add to that as well, I think this new European initiative, the IAMI, the Innovative Advanced Materials Initiative, I think hopefully that can drive more opportunities for these kind of projects. I know one of their strategic areas is construction, so hopefully that will lead to us being able to do more studies in terms of the nano safety and exposure of of graphene in or other advanced materials in construction products. So I think that's something still in early phases, but hopefully in January that initiative will be approved, and we can then look forward to a new ecosystem within Europe to drive these things forward.
Yes, Stephen. I see a comment from Sean. Sean, you have the floor for 1 minute because we need to leave. Oh, sorry, Anna. Yes, go for it, please. Yes. Mm-hmm.
No, I just wanted to, thanks for mentioning it. I think it's also a good initiative in a way, but on the other side, I understood that the regulators cannot be part of it. So that's a bit of a pity for us and also for exactly that connection of industry and science and regulation. Just wanted to add this.
Okay, that's a good point. Yeah, thank you, Anna, for this. Sean, you have 1 minute if you want to highlight your comment on the chat before we have to move.
Yeah, hi. Yeah, it was just sort of say, how can we then? We've agreed that it shouldn't be a them versus us kind of situation, but it still sometimes gets portrayed very much that industry's trying to always avoid regulation. So how can we make sure that this conversation gets out into the wider world sort of better?
Indeed, that we are working together, right? Not like in different worlds. Yes, I agree.
Yeah, it's not a siloed conversation of you have regulators good, industry bad.
Yeah, fully agree with this. We can see from today's presentations that we are working together also in different initiatives. Thank you, Sean, for this. I need to move on now to Damiana. She's chairing the next session, talking about the very interesting topic of using modeling tools for risk assessment. So I'm really looking forward to this new set of presentations, and many thanks for the speakers today for these very nice presentations and for keeping the time. Thank you so much.
Thank you very much. Hello to everybody. I'm chairing the second part of the day today. So I'm very happy that we have a lot of very good speakers, and thanks to the audience. I've seen that there's a good discussion. Hope there will be the same at the end of this session. We have 2 lectures before the lunch break, then we have a lunch break, and I'm happy to announce the first, Agnieszka Gajewicz-Skretna. She will tell us about read across and grouping, what we are very interested, whether it works or will work also for advanced materials for graphene and this type of material. So Agnieszka, the stage is yours. Thank you. Agnieszka, are you with us?
So I cannot see Agnieszka in the list of participants currently.
Otherwise, we just go to the second presenter.
Yeah, I think Asmus is here. Maybe we can start with Asmus and see if well, we lost Agnieszka.
Okay, good. Good, Asmus. Just finish your
I'm still doping.
No problem. So we go now directly to some new techniques, in particular microscopy techniques. We are happy to have these because it was mentioned a couple of times before that we might need more microscopy, spectroscopy, these type of techniques that are in a way more intuitive, straightforward to show us something. And yes, we would really like to see how the computational approach and modeling could fit with these techniques. So Asmus from BAuA. So let's start with you. Thank you.
Yes, hello. Thanks for giving me the opportunity to present our work here. It's on it's on advanced computation methods for automated correlative microscopy of advanced materials. Of course, this session is about advanced materials. Brief disclaimer: I'm not really a standardization guy. I'm more the tech guy doing the method development and coding. I have some colleagues who help me in doing this and who drive this forward. So John, Tom, Hannes, Nico, Carmen, and Kerstin, just to briefly mention them. I'm working at the BAuA, which is the Federal Institute of Occupational Safety and Health, located in Berlin. And here are just some of images of our instrumentation. We are using 2 microscopes, SEM, Raman microscope, and our useful tool, the GPO workstation. So now, just to get into the topic of advanced materials, my personal favorite definition for advanced material is that an advanced material is a material with more known unknowns than known knowns. So on the left top, you see the sky disk of Nebra from the Bronze Age. This used to be an advanced material at that time. It is no longer. It's a standard material. And so we should aim at developing advanced materials into standard materials. And my way to bring this forward is to develop advanced methods into standardized methods. And I hope for your help in doing so. Correlative microscopy aims at correlating several information layers. That's the main idea. It's generally a spatial correlation we need, and it's already quite well established for some type of analytical microscopes. On the left, you see the SEM-EDS combination, which is a standard which can perform elementary analysis. On the right-hand side, you see the Raman imaging, where you can overlay the optical image with Raman bands, which you might filter out from a signal and highlight. On the right-hand side, you see macrophages that have been exposed with carbon nanotubes. On the left-hand side, it's paint sample from one of our colleagues' home when he was renovating his doors. So it's traditional paint. I will come to this perhaps later in more detail. So the problem is to correlate the images from different microscopes. Here we have on top the SEM image, on the bottom the optical microscope image. Let's see whether I get a pointer. They look quite different. The human brain is capable of finding similarities, but we need to get this into software to perform this correlation. And one approach is to do convolutional operations and matching of templates in order to readjust the stage of the microscope to higher accuracy to become able to overlay these images as shown on the right-hand side. So this is a transparent overlay of the two views of the same nanotube on a porous filter. What we really need is that we want to identify advanced material objects and to compile comprehensive data sets that allow to do so. This is especially interesting for objects that are too small to be resolved by optical microscopy, as is shown here in the center image. You don't see the nanotube in the center of the image in the optical microscope, but we can localize and visualize it in the scanning electron microscope. And so we know where it is. And what we are using is the Pohl pattern, which is a unique random pattern to make up an additional local coordinate system, which allows to overlay the or to find the Pohl constellation we see on the left image on the less resolved optical image. And this way we can perform Raman imaging of an object we don't see. And you see the Raman G-band response of the carbon nanotube on the right-hand side in the overlaid image. So we were able to identify a material which we couldn't see in the optical microscope and which we couldn't identify in the scanning electron microscope, as it is composed of carbon, and EDS doesn't help. Here's just a a nice view graph of what you can do, for instance, with early exposed macrophages that were exposed to CNTs. There are different levels of layers of information, the low voltage SEM image, the optical micrograph in AFM, image of the scenery of the macrophage. We overlaid the Raman G-band so we can localize carbonaceous material inside or outside the cell. So we are interested whether the material is inside and outside. And here on the right-hand side, you see the 3 different information layers, at least for without Raman, in direct comparison, and they can be aligned by the help of the features we see in the image. So this is done manually, this alignment, but of course we are aiming at doing this automatically to acquire representative statistical information and tell about the source and fate of advanced materials and study toxicological effects. So advanced correlative microscopy aims at visualizing micro and nanoscale objects collected, for instance, on filters or in cells and tissue, identifying them with respect to material composition, product identity, or identify the emission source, as is important in the occupational scenery. It aims at classifying objects with respect to their identity, morphology, and hazard characteristics, quantify them to estimate the exposure dose, especially of hazardous fractions, and observing the fate of these hazardous fractions, for instance, with biokinetical techniques in cell experiments, as for instance was shown yesterday very nicely by Robert Lansiedel in these time-lapse videos of macrophages trying to incorporate fibers. And in the end, we need to document all the information. And this information is highly diverse and highly complex, and it needs to be stored in a sensitive in a manner and must be findable according to the FAIR paradigm we are trying to follow. So we need, on the right-hand side, coordinate microscopy. I will explain this in a minute. We need spatially correlated analysis, as I have shown you already. We need computer-assisted tools for object recognition, analysis, initiation and interpretation, and the classification. We also need to interpret and execute counting rules, well-defined counting rules. And we desire to get hold of automated techniques that allow to aggregate good ensemble statistics to really nail down the concentration of the hazardous fraction with good reliability. And we want to perform flexible analysis workflow. We need data conversion tools, evaluation tools, review and presentation tools. So there's a lot to be done. We have developed some software in-house at BAuA. One tool is called TINA. It's German abbreviation for stage navigation. And there we start with every sample to assign to this sample a coordinate system. So this coordinated microscopy, whenever you image something, you need a coordinate system to find your objects back on a second analysis run you're performing with your sample. So we just create pinholes in the sample. We measure the location of these pinholes with respect to the stage coordinates of the system, and then we can perform automated image acquisition on random or selected spots on these samples. This is a gold-coated nucleopore filter shown here. And of course, we calculate the affine transform between the sample coordinate system and the microscope's coordinate system. We have also tried to develop different techniques to do the high resolution spatial correlation. As I explained already, these Pohl pattern to find them on the different microscope views at different resolutions to match them. We have developed an algorithm for what we call Pohl constellation matching. It's like the Big Dipper in the sky. You can recognize it easily due to its characteristic pattern. And so we are looking for characteristic patterns in these samples to overlay the images. Of course, you can also work with object feature matching. All aims at high resolution local coordinate systems that allow to overlay the information even of very small scale objects. As we are dealing with large filters, relatively large filters with respect to the particle size, it's a tremendous work to find these particles on these large filter areas, and we have therefore developed artificial neural networks, convolutional artificial neural networks that are capable of finding particles on the type of filters we are using, these nuclear Pohl filters. They have been trained with about 20 gigapixels of annotated image data and work highly reliably on the close to pixel accuracy. Whenever such a segment, as we call it, was found by the neural network, we trace its shape and interpret its shape using an algorithm. So the algorithm follows strict rules we have defined to find the backbone of a fiber and to disentangle crossings of fibers using the direction of the end pieces of the fiber to connect them, etc. This way we get a list of objects. It's a kind of two-step instance segmentation, but only one step uses neural network. The other part is done algorithmically. We also have defined different counting routes. Here is shown one of them just to show you the complexity. These counting routes have to be translated into code and rely on the interpretation of object morphologies in order to decide whether the object has to be counted or not. And of course, algorithmic tracing is complicated, and in many cases, even the human brain is not capable of disentangling the different morphologies you find. So we are also studying, therefore, how well the automatic approach and the human approach correspond when interpreting complex morphologies, and whether the count results correlate. The next step, after we know the morphology of an object, and for instance, we can select on a special morphology like fibers, so our group is highly interested on fibers, we can decide whether we perform object-specific additional analysis, for instance, EDS analysis or Raman analysis. So we initiate this object-wise after this first morphological classification was performed. Then we obtain a spectrum, and the spectrum can be interpreted. There are different techniques. So you can do elemental quantification, for instance, for EDS. You can follow routes, like, for instance, the asbestos identification convention, which is established in Germany. We have translated this also to code, to automate the interpretation. It used to be an Excel sheet, spreadsheet to be handled by the operator. But we also are studying attention mechanism-based neural networks to do the direct interpretation of the raw EDS spectra. And this can be done with very good success. This is just a small excerpt of our work showing the asbestos fibers, the 6 different compositions, and we get close to 100% reliability and accuracy for the neural network we have trained, but it also works for about 70 different mineral fiber materials with high accuracy. Yeah, but the main idea behind our work is to automate everything, not to automate just one standard operation procedure, as we are using our machinery also for research into ensemble characterization, for instance. So we need flexible analysis workflows. And the idea was how to design these workflows and how to automate them. And the main backbone of our approach is a database we are developing. We call it FAMOSH, database for fibrous and advanced material occupational safety and health database, an acronym. And this database somehow holds code-like database entries which define what operation is to be followed. And these operations are then unrolled into database entries. So if we acquire an image, we don't know yet how many objects we will find on this image. So we define that for each of the objects, a certain analysis is to be done. And then the database creates, as soon as it is known how many objects were found by the neural network, it creates the entries in the database, which later on hold the subsequent analysis information. So every analysis step and every datum is directly linked to its entry in the database. And for the non-experts, we decided to use a children's programming language. It's a visual language to design such workflows. It's not yet fully operational at the moment, but we plan to roll this out in half a year approximately and make this available to others. Yeah, but in the end comes the important question: what format to choose to store the data in and to hold it in the database. And there we aim at using the FAIR data formats, which have been developed to great extent by the FAIRMAT consortium, which started with the Nexus data format and developed specific formats for spectroscopic purposes. So there's, for instance, NX-Raman Nexus format for Raman data, also for electron microscopy. There are formats, and they are going to be standardized or are partially already standardized, because our pain and our work is really to interpret the manufacturer-specific proprietary and often binary formats, and to do reverse engineering to get hold of the data we produced during our analysis runs. So I'm running out of time. So the conclusion is we have a roadmap towards standardization, but standardization requires validated reliability and accuracy. That's especially a challenge for AI-based methods. We need to collect arguments for their trustworthiness, but also multi-parameter algorithms need to be trustworthy, and we have to show this. We intend to develop our machinery further. We applied to advanced materials in research projects like polyresonant macrame, and we focused on the automated characterization, especially of thin asbestos fibers in the light of the new EU regulation, and machined carbon fiber reinforced polymers, plastics. We will provide SOPs for our techniques, participate in interlaboratory and round-robin tests, And we will benchmark human and artificial intelligence with respect to classification, differentiated counting rules. We will invite material experts to review content of our database with respect to image segmentation accuracy, object classification, reliability, and image annotation quality. And this way, we hope to make the database to become a source of reliable information and to assess also, especially the quality of different correlative analytic microscopy approaches, and it might become a source for training data for neural network development in the future. Thank you.
Asmus, thank you very, very much. I put down a lot of things that might be interesting for the discussion. Hope that you stay with us. And now, if there are any quick questions, I would like to ask you, just switch on your microphone and ask. No, if not now, then perhaps later. I have just one question. Asmus, what's the state of harmonization of sample preparation and then method standardization? What's the progress in the area of microscopy and the spectroscopy?
I'm not the expert to answer this question. I fear we have colleagues in our group, so you know, Anna and Elisabeth, they are developing these topics further. We have, of course, standards for collecting samples at workplaces. We follow these standards very strictly when we determine exposure levels at workplaces. We have colleagues working in the field to perform such analysis. And yeah, but that's always the starting point to get sample. But we are also dealing a great deal with material samples we prepare in our laboratories. We have dusting methods, dispersion methods, and we collect these samples on filters to do these ensemble characterizations and to learn about lengths, diameter distributions, etc. And there we follow in-house standard operation procedures, how to collect the samples and how to disperse or release them in dustiness tests, for instance.
Thank you, Asmus. So this is just one topic for the discussion later, and the other one, probably the data verification, yes, but we'll keep it for later. So if Agnieszka is not with us, is Agnieszka with us or not yet? If not, then I ask you, Dan, if you don't mind to move your presentation to the now, not after the lunch, okay?
I am prepared, yeah. And
you're prepared as always, Dan.
Has warned me.
Thanks a lot. So it is Dan Hodoroaba with us from BAuA, representing Project Accords, and will share also with us the approach of this project on data correlation and imaging of advanced materials. So Dan, the stage is yours. Thank you.
Thank you very much. I'm happy to see and recognize some of you. And I'm asking what is better, to be the first after the lunch or the last before the lunch now. But I hope I can keep the time and give you a good overview on the challenges, but also successes in correlative imaging of advanced materials. We have seen in the talk of Asmus, basically fibers. I won't show any examples with fibers, but on nanoparticles and generally on advanced materials. So different examples. I will start with a short explanation of what we understand by correlative imaging. We have seen just one possible combination in the electron microscopy with the light microscopy, but there are much more options. I will show the virtue of exploitation of these different methods or different signals or operating modes in one instrument. As said, I will show examples. putting the focus on challenges, as said, particularly on nano materials. I will put the focus or staying with challenges on the sample preparation, what is definitely one of the most challenging parts. And I will bring some metrological aspects looking forward to standardization, and also referring to some reference materials, also one point discussed here today. I don't have the time to go into too much details and too deep, but microscopy has started a lot of time ago. Serious discussion studies about correlative microscopy or imaging have started in the 80s, with the basic, or say the starting point of correlative analysis being what we have seen in the previous talk, combining or correlating light and electron microscopy. And you see here different views in or using different instruments, or combining, correlating different operating modes or methods, microscopies in the same device, in the same instrument. This analysis of the same location, this is the quintessence of essence of correlative analysis. Analysis of the same field of view or area on the sample. You see here a plethora of all possible methods, each of them being able to analyze, to address one or more properties. Yeah, one method is no method. It is a saying here at BAM, and each method can analyze something specific. And it is the duty of the expert working with the method, finding out and controlling all of this descriptors, what each method can, depending on the resolution laterally in the depth or elemental sensitivity and so on. Possible options of correlating methods, you see here just a few. Maybe for more details, you can check this publication here on the bottom of the slide, where already 6 years ago, it was published a correlative microscopy roadmap. And you see here different acronyms, and you recognize some methods. Basically, you can combine almost all possible or any two different methods, meanwhile, with a more or less effort, and more in one instrument. Coming to microscopy, now to electron microscopy, and without going too deep into details, I would like to show you 2 examples where you combine 2 different operating modes in the same electron microscope. High resolution mode with a so-called top view mode, having the right electron detectors, and the transmission, so-called transmission mode, almost like in an TEM. And if you combine these 2 working operating modes, you see here 3 examples. You see the disadvantages and advantages, and the advantages by putting all together. On the upper row, you see examples where the surface is very is sensed with a high sensitivity, is analyzed with a high surface sensitivity. You see details here on the surface, like roughness, also what you don't see in the transmission mode. On the other hand, in the transmission mode, you see hidden artifacts. You lose what is on the surface, and it is a very good tool, analytical tool, to perform metrological dimensional measurements. The edges, the boundaries are better defined. The contrast is superior due to the physics behind, physics of the signal. We stay with this pair of correlative microscopies from the top on the left side and in transmission. And you see here the idea what I have meant earlier, that now playing, let's say, optimizing the individual parameters at an instrument like the high voltage in an electron microscope, you can then perform accurate metrological measurements of the length, for example, of the size and then of the shape. And you see here that high kilovolt and low kilovolt, they will result at the end in different results regarding, for example, the length of these particles, of the same particles. You can perform, by the way, this type of analysis simultaneously with the same excitation electron beam. We come now back to what I have said at the beginning, correlative analysis of the same area, of the same sample in more instruments, in a TEM here on the right side, in an SEM with different operating modes on the left side, and imaging the same nanoparticles, and you see, or the same nanoparticle, and you recognize immediately the advantages and disadvantages. And let's say to come from the 2D observation, projection information up to a real 3D extracted information if you use, the so-called selected area electron diffraction, SAD mode or method in a TEM. We have heard already about also EDS correlating with SEM and depending or having also not different morphologies being visible by microscopy, but you see immediately also the elemental composition or distribution by performing the so-called EDS maps. Or like in this example, microscopy on the left side of nanoparticles without a shell here, not being visible, but making the shell visible of approximately 10 nanometers, if you have the right tools, being visible with the X-ray spectroscopy attached to an SEM. So very good completion of the two methods. I have said at the beginning that one challenge, very important, crucial step for an accurate analytical result in the nanoparticle analysis is the sample preparation. Two examples here, silica bimodal nanoparticles and titanium dioxide bipyramids. You see here, if you use the appropriate sample preparation, you can separate, isolate almost perfectly these particles on a substrate, and then you make the door open for accurate and quick automated analysis of the images. This is the result of the analysis of this bimodal, for example, silica material, where we expect 1-to-1 modal concentration of the two modes, something like 30 and 60 nanometers size. And you see here that most of in an interlaboratory comparison, most of the participants and also different methods, but basically imaging, underestimate this concentration, this ratio. Why is this? By using different descriptors, because you see here that the sample preparation, the isolation of the nanoparticles of single nanoparticles on a substrate, it's not perfect. You need this perfection. So you see here some dimers of the smaller fraction particles, with the result that at the end you will underestimate the number of the smaller particles, which is a typical effect or artifact in imaging. So even more effort must be put into the sample preparation to improve this, to bring this to perfection. I come now to an example from the 2D world, graphene oxide. where in the usual case, sample preparation, you have something like this on the left side. And if you invest in the sample preparation, you can get, again, not a perfect, but a quite good qualitative image or sample deposition so that you come with different approaches and analyzing accurately the right descriptors. By the way, this is another interlaboratory comparison. You see here different logos, but coming from metrology projects, European projects, and the results will come into standardization. You see here the number of the standards where this results and knowledge as a guidance at the end will come into. If you want to address the height, then you need other methods. Here is only the lateral dimension. For example, Raman, yeah, we have seen already a little bit of Raman, but without coming into details, you see here already a few years ago that this correlation, also microscopy SEM of graphene, for example, several layers here with Raman, it is a well-working one, particularly for these 2D type materials. And then I have also shown that staying with imaging and with the good nanoparticle deposition on a substrate, you can apply then different imaging techniques, not only SEM, where at the end you have 2D information projection, but gaining more and more information regarding the 3D shape, particularly of complex, more realistic samples. They're coming away from this spherical monodisperse samples. And then you can extract the real 3D shape with the real size also. One quite new method, staying at an electron, scanning electron microscopy, is the so-called transmission Kikuchi diffraction. Maybe some of you have already heard or have this method coming from the backscatter electron diffraction, a conventional technique at an SEM with micrometer resolution, special resolution for grain size typically of metallic alloys, but coming down again via appropriate sample preparation as a thin sample and coming down to nanometer resolution. You see here again titanium dioxide bipyramids, 40 to 60 nanometers, and you recognize it over a scan, only with one scan, quick scan, important, how the particles, how large they are and how they are oriented on the substrate, again, with 3D information. And I come now to the so-called chemical maps. Not only the morphology, but the chemistry is as important as the morphology, and this both two aspects, properties must be correlated. Of course, you can apply EDS, what we have seen already several times with an electron microscope, and recognizing enrichments of concentration, in this case of porous thin films, iridium oxide, titanium dioxide, and you recognize inhomogeneities in the elemental distribution coming from the synthesis. And you can use more advanced and more complex advanced methods for the chemistry, in this case, analyzing the same area of the porous thin films with these islands, with iron oxide enrichment, with the secondary iron mass spectrometry applied in the imaging mode. And again, you see in the first nanometers what happens. And if you have the right tool, the methods are there, are available. The Auger electron spectroscopy, one method being very sensitive regarding the lateral resolution of a few nanometers. You can put your probe, your beam, on exactly on such an island or in a pore or wherever you want at the nanometer scale, and go into the depth by sputtering and recognize what is the distribution of elemental distribution, what is the chemistry in the depth of this thin films of approximately 120-30 nanometers. And the very last examples, maybe for Stephanie or for ink, for a commercial product, how to test the homogeneity of graphene flakes, for example, in an ink, in a commercial ink. We have applied SIMS, secondary ion mass spectrometry, in this mapping mode, imaging mode, and you can correlate, or first point, you see a homogeneity of the distribution of the graphene flakes, in this case, functionalized, fluorine functionalized, and you can correlate the chemistry with the morphology in an SEM. It is a good result coming from materials investigated in our Accords project. And this was my last slide with examples. So that at the end, we can say that imaging is a very useful tool, is more and more used to get as much as possible information. You have to be careful that mostly you have 2D projection information. We have to come back to 3D and correlate different information from different methods. We have to think at the representativity. We have heard today about tons of materials, but we analyze here hundreds, maybe thousands, tens of objects. Each method, imaging method, has its own resolution, laterally in the depth, sensitivities, and so on. We need experts to control very well these methods and provide the community with guidance. We have to invest. One of the biggest challenges is the sample preparation. And we have heard today about automation. Also, the sample preparation, I think the automation of the measurement is the easiest part. The automation of the analysis and the interpretation of data is as challenging as the pre-step in the sample preparation. And we have seen already examples that many groups in the world are working on software, on format of the image files, on the chemical part, on the morphological part, but only part of this is standardized. Please stay active and work so that we work together. No individual solutions, please, to go towards standardization and dealing with this large amount of data, so that in each pixel, having also 3D information, we have a spectrum at the end, or even more information. With this, I thank you for your attention. I still hope that I am in time, and I thank you some funding parties here behind the results.
Thank you, Dan, very much. Are there any quick questions, or will we keep the discussion for later? If not, then I ask Elizabeth, is Agnieszka with us, or she will not join us?
I didn't have any response from Agnieszka,
Right.
so I asked all the presenters from this afternoon.
Right.
They can go 20 minutes early, so that would be the plan. So we would have 20 minutes more for the discussion in the end, and be under a little bit less of time pressure. That's the plan to go for.
Then it is time for a lunch break. We are supposed to be back at 1 o'clock, so they will be very short, and we expect, please come back. Janez Štrancar will also give us one very interesting perspective on application of imaging methods, a little bit other view as these two. Thank you, and see you at 1. Thanks for now.
Time also
okay. Yes.
For the presentations, a couple of minutes or so.
Right. So thanks for informing us. We hope there's nothing really bad happened, so that she could solve the situation. It happens sometime, that we just need to do something or solve something. Otherwise, I would like to start the afternoon session, if you all do not mind, and I would like to invite Janez Štrancar. You have a pretty long title of your presentation, so I'm not going to read it, but it is very interesting, your automated time-evolved microscopy. for the purpose of imaging materials, advanced materials, 2D materials. So Janez, thanks for joining. Thanks for having this presentation, and the stage is yours. So, 20 minutes, and if you need a minute more, you are more than welcome.
Thanks. I will start sharing. So let me see. I think you see my screen. Hopefully.
Yes, everything okay.
Okay, perfect. Yeah, the title is still long, but actually the second part is most important. So I want to focus on how to do long-term hazard assessment. So that's something which evolve on months or in months or even in years. Yeah, so this is what we mostly focus on. So we mostly focus on disease that develop slowly, and the disease that are even modulated, treated slowly. So, and the way how we solve that approach is by simple concept. We think, okay, every big fire start with a small spark. Yeah, so that's if we understand the conditions under such a spark propagate into a big fire, then in principle we can beat time and can deliver long-term hazard assessment ahead of time. So basically what we do, we shrink the observation to, let's say, a day or a few days. So we observe in vitro the different responses of biological system, and then translate these into mode of action. So basically in silico and propagate in silico. So we do practically the same stuff as physicists normally do while they solve the equation of motions. So the same way like we predict weather days in advance, or the same way how we predict trajectories of a spaceship reaching, I don't know, far planets. Yeah, and that's the only way how you can beat time. In principle, you have to learn the equation of motion, which is in case of toxicology actually a mode of action, and then you have to learn how to propagate this mode of action in time. So instead of waiting an animal that it expresses adverse outcome, we predict this outcome by NAMs, which is not only validated, but it should be validatable. And I will try to address also this issue shortly. The basic proof of concept we defined in our paper published in Advanced Materials in 2020. So I will not go into details of the first half where we present how we discover one of the mode of actions, but I will just go to the hidden message, which is that if you know the early mode of action, then there exists a mathematical description for time propagation of this mode of action. And we showed that in that paper. We showed, for example, that if you measure few in vitro properties of in vitro system, then it is possible to propagate this in time. In this paper, we propagate it for 2 weeks in advance. The problem with that paper is that we have used enormous amount of resources. So this was part of the Smart Nanotox project. Many groups were involved, 34 different experimental methods in silico, in vitro, in vivo, time-lapse microscopies, high-resolution advanced microscopies, correlative microscopies, OMICs, a lot of researcher resources. So altogether, my estimation is direct cost €2 million for this paper. It's really a huge one, but indirect, it's even more. So the problem is that this is unmanageable. You can't really rely on all that information to derive early mode of action, because if you spend at least €1 million per mode of action, we are going nowhere. But you need mode of action at least in some to some degree known, if you are willing to do time propagation. So yeah, and while I'm speaking about validatable nums, I mean first the number of degrees of freedom. So if we stay on molecular level information, so like genes, proteins, lipids, I don't know, nucleic acids, signaling cascades, ways how these specifically interfere with each other. So we are ending up with at least 100,000 degrees of freedom, if not more. So which means already during the first day after triggering the initiating event, it can be about 10 to 10, even to 10 to 15 different pathways possible in this problem phase space. Of course, we can't really possibly detect this number of pathways, and we can't characterize them. So the knowledge is pretty segmented and far too complex for a validation. So what we are doing, we are going one level up and observing things on the functional level. So effectively on the level of functional units of a cell. So you know them by name organelles. So we follow organelles and functional responses on the subcellular level, endocells, and on the cell level, and on the level of cell-cell communication, but without specifically focusing, for example, on one protein. Let me make an example. For example, cell-cell communication, you can focus that one type of cell excretes certain type of cytokine that is then bound or triggered another type of cell. So instead of focusing on that level, we say, okay, we track the vesicles that can contain many different messengers, signaling molecules, RNA, DNA, proteins. So we don't discriminate what is the message, we just discriminate the messenger. Okay, so in our case, we split the observables into 6 groups. I will not go into much details, but there are one very obvious, which are different cell types. We always include structural and immune cells, and many times also plastic cells in the platform. Then we colocalize these platforms with the trigger, which is either nanomaterial, material, micromaterial, chemical, vaccine, or so on. Then we have the third group is damage to the functional units, and then response of those functional units, response as a cell as a whole. So it means, for example, taxis of immune cells towards the structural cells, building of extracellular matrix and similar, maybe multinucleation in case of cancer and stuff like that. And then cell-cell communication, which I have already addressed before. So what we basically now, this looks pretty very much similar to like cell painting, but there's a major difference here. We search for patterns in time, not only in time and space, and not only in space. So that's we believe it's key for validatability. So patterning in times allows physics-based model constraining. So we are not predicting the state of a system in the future based on patterns now, but based on dynamics now, how things are coupled. And this is exactly what the equation of motions are, how they are defined. So, for example, here on the left would be a static monitoring of cells and their structures. So you would be able to determine many patterns matching in space. But instead of static monitoring, we go to live. So we track cellular response live. And then, of course, we know when things happen and how they happen with delay to each other. Now the entire process is built of the following steps. So first we take cellular device, we expose it, we monitor its evolution continuously for at least a day. It depends on the platform. Some platforms are faster, some are slower, but normally it never exceeds 3 days. Then we have, we predefined the algorithms for quantification, like it was already also said in one of the previous talks. We use that algorithms. For example, on the contrary of cell painting, we do not derive many patterns, but we search for specific patterns that earlier, by preliminary experiments and within scientific papers, we prove they are relevant for the evolution of a disease. So after we have this monitoring done, we go to quantification. We quantify all the images, derive these observables, which are like key events, sort of, and then we translate their dynamics into equation of motions, which we call the interaction model. And this is actually representing the early mode of action. And after we have that, we can propagate this in time and then derive standard toxicological assessment like dose response, time response, or like the way how, for example, inflammation resolves with time. And also both information together. Of course, part of the mode of action is calibrated against the in vivo data sets. So it's also built in back into this equation of motion. So that's why we need calibration and validation of model. I would just stress that entire translation into mode of action is unbiased, while the upper part, the red one, is material specific, while the lower part is material agnostic. And what we are basically doing here, we are determining the first arrow of the AOP concept. So the first arrow from molecular initiating event to the first observable key event is actually material specific, while all other key events, according to AOP concept, is material agnostic. And the problem is that materials many times specifically trigger specific responses. And of course, events like damages are very much material specific because they are driven directly by physical interaction between the surface of nanomaterials, for example, and biological systems. So here are some numbers that you will get, you can imagine what we do. So during, for example, 24-hour time experiment, there are different time points, many channels, optical sections, scenario, and we acquire roughly 13,000 images, which means about 3 billion data points. We quantify them into up to 20 observables, which have several thousand evolved values and derivatives. And then it's important that what the translation methodology do, it condenses these values into correlations in time. So there are about 20,000 condensed time correlations. And then with predefined interaction models, it gives us about 100 to 150 in vitro material-specific interaction couplings. And then from calibration method, which is this loop, from the end, we add additional 10 to 20 calibration-derived material-agnostic couplings. So we have then at the end about 150 to 170 couplings altogether. And this is by this, then of course, after you derive the mode of action, it's just a matter of few hours on a big computational machine that we can deliver prediction of adverse outcome in less than a week, for example, up to 6 to 12 months ahead of time, so in average 9 months. And that's, for example, enough to predict chronic inflammation. So here is just illustration how calibration looks like. So we take a group of materials with complete in vivo data sets. This we are doing now in NanoPass consortium. So we take complete data set means that we need to have at least 3 doses and at least 3, better 4 or 5 time points, long-term time points. And then we calibrate this small calibration segment of couplings against entire group of materials. So we fit all their dose dependencies and all their time dependencies at once. So just to repeat, for every material we make in vitro monitoring, but calibration is done only once for all the calibration database. So currently, for example, this is how calibration looks like. So ideally, we calibrate and validate against the key events such as neutrophils influx into the lung. So on the x-axis is this quantity measured in vivo. On the y-axis is predicted value, so in silico. After doing in vitro experiments and in vitro to in silico translation. And ideally, all these dots would lie on the diagonal if they would have zero experimental variability. And typically, these gray lines are the typical variability of in vivo data set. So you can see this is about 20% error. So basically, you cannot really fit the calibrated and validated model outside that diagonal zone. Although, for example, if I take binary prediction model F, so if the prediction model would be binary, then entire dashed area would be true positive and the small one true negative. At the end, I would like to maybe to present what kind of results this can be used to deliver. So the first is obviously standard dose response for different time windows, and then for any selected time window, for any selected dose, we can deliver the inflammation resolution, so the time evolution of the outcome, and then we can also merge them together. So in a form of contour two-dimensional plot, so the time is on the x-axis and the dose is on the vertical axis, and then the coloring is, for example, inflammation intensity in terms of neutrophils influx into the lung. So you can imagine that the green area is safe, the red area is very intensive inflammatory, and the gray line represents the low L value, which is time dependent. So the left graph is for single exposure, so that's typical results that would classify or assess like an accident, so single exposure, and the right one would be like a continuous exposure, so where you build up a dose slowly with time. And then, because I said we derived also mode-of-action information for each of the model, each of the observable we measure, we can also predict how it evolved with time and how these observables couple to each other. And then you can represent those arrows in terms of map, which is something you're more familiar with. So it's an AOP-like network. So basically, in our experiment, you have to come from the exposure, which is one of the two boxes here on the left, to the neutrophils influx, which is this blue box here on the right. So in principle, in the current database, by just taking, let's say, 20 to 25 materials, you can already cover of almost 70% of the key event relationships. So basically, this network represents the first arrow in the AOP I said before. And many materials induce different early pathways, and but many of them are shared between the materials, not completely, but somewhat. Yeah, so I would like, at the end, I just, here it's an example of first cross-species double-blind validation. So we take the mice calibrated model, the mice data, and we predict the red dose responses on the left, and time evolved on the right. So together results are on the far right. with different semi-continuous or repetitive those experiments, and you see that the match is quite nice. So maybe we discuss that later. So thank you very much for your attention, and I will of course be happy to answer your questions.
Janez, thank you very much. You are very much on time. So are there any questions? Just switch on the microphone and ask if there are any questions. We do have time. No questions so far. Janez, I do have one question. You very nicely showed what you are actually measuring, detecting. So what parameters are you somehow, let's say, recording? How to link these measurements with, let's say, inflammation? Are you then using data from the literature, so in silico approach, or are you have some specific biomarkers that direct you in one direction?
For example, I give you the example of neutrophils in flux. So what we do, we predict the first key event, which is confirmed in the AOP, for example, now in case of inflammation. So we take the AOP pathway, we take the earliest key event observable in vivo, which is in this case neutrophils influx into the lung, and we predict this key event. So then we take, okay, if we predict that key event, the AOP is followed, is evolved further into final inflammation. So we use the AOP concept. We just unravel this, the first arrow, and make it quantifiable.
Okay, and you are actually recording images, is that correct? And then
we are recording evolution of images, yes.
You're recording evolution of images, and you are recording different parameters, so different changes you can record. Are you using stained cells? Probably not. You're still alive because you are measuring continuously for 3 days.
All live, yes. So we also exclude many of the classical fluorescence probing, which somewhat or somewhere interfere with live imaging. So we are pretty very much picky about what to use to label those responses. Yeah, and it's not just confocal fluorescence. It's a combination of confocal fluorescence and backscattered microscopy, which are taken to be the cheapest and the simplest and the most transferable microscopies that are live compatible.
Thank you very, very much. Extremely interesting approach. Any questions? No. Are there any?
I have put something in the chat.
Yes, done. Just.
Okay. Thank you, Janez, for the talk. What is not very clear to me, maybe question continuing the previous question. You are using basically light microscopy, as far as I understand. But regarding now, we're talking about the materials on the nanoscale in the few nanometers. How do you consider this, or how do you make sure that with light microscopy you don't lose maybe the very small fraction of nanofraction? How relevant, or how do you consider, how do you include this in your model? This is unclear to me.
Yeah. So basically, with backscattered microscopy or any confocal microscopy, you can detect directly particles down to 100 nanometers. Smaller particles. Well, smaller particles are detection of smaller particles are basically calibrated with the use of super resolution microscopy, again live microscopy, and then transformation to backscattered. The simple trick is that you have always a distribution. Even if you have very small particles, they always aggregate, so they always make a distribution of sizes. So basically, we never are really too much worried about that we will lose the single, for example, nanoparticles. because as soon as you go into a biological system with those buffers and many biological molecules present, they somehow even further aggregate into smaller or bigger particles. You always have a distribution of size. So independently, whether you're monitoring perfectly small, very small nanoparticles, you will always have a fraction of a little bit bigger aggregates that are capable of tracking with backscattered microscopy.
Okay, thank you. It is an interesting approach. Yeah, you are working with an assumed particle size distribution. Yeah, you have some models behind. Yeah, it is efficient, but it is an assumption to me.
We always measure it directly from the images. You just miss the very nano, so the part which is normally, if you use confocal microscopy, you miss the part somewhere between 100 nanometers. So if you use super resolution, you miss the part between below 20 to 30 nanometers. But that's more than sufficient for practically everything.
Okay, thank you. Mm-hmm.
Actually, Janez, you're measuring the effects, not that much the particles. Am I right?
Exactly. Yes.
So therefore, you are not that much concerned about, what is happening with particles. You're just assured that the cells, your system is exposed, and that's it. And then you measure all sorts of different parameters, or let's say different responses, and then you link these to the existing, let's say, understanding of the adverse outcome pathway. Yeah.
Yeah, that's why exactly we are not, we do not really care whether we have a single well-defined species of nanoparticle. We can work on cocktails. We can work on even mixture of nano and micro particles, whatever it's relevant for the inhalable or respirable fractions.
Right. We do have one question in the chat, and I think you partly answered. So the question in the chat is, how do you validate or link your platform with human effects prediction? So how do you link it? Could you also again answer this, how you link it?
Yes. So of course, first we link prediction to mice data. And then we link mice data or together with different platforms to epidemiological or clinical data. For example, in case of neurodegenerative diseases, we have directly the clinical data, the epidemiological data. In case of osteolysis, for example, we have clinical data. So it's different for every platform is a little bit different.
Okay, but in fact, you measure a biomarker, yes, and then you link this change in this biomarker to a response of, or I mean, to some clinical whatever consequences. So you actually need, or you have identified these biomarkers that might be related to one, let's say, health outcome or something.
Yeah, we measure dynamics of a set of biomarkers, their delays with respect to those early key events that are measurable for AOPs.
Thank you. And I see a hand of Antje. Antje, just go on with your question.
Yeah. Hello, everybody. I'm not Antje, I'm Martin Wiemann, sitting on his place. Sorry for that. Yeah, thanks for the brilliant talk. So many questions. So one is, how make you sure? So there are so many different cells and cell lines around. How make you sure that you're dealing with the right cells? Are you working with primary cells, with cell lines? And how make you sure that they have the right properties for predicting what is finally going on in human tissue? This is my first question. Secondly, concerning dosimetry, whenever talking about effects in any organism, it's a matter of concentration of particles in the tissue or even in the cells, which usually is very low, even under constant exposure condition. We measured that, for instance, for cerium oxide all over the red body. And dealing then with cells means that if you want to see some effects, you have to go to quite high doses, which in the end are not really relevant for what is going on in an organism on the long term. So how do these different dosimetries are matched in your model? How do you consider that? And then the third thing is about the dynamics. I mean, the particles in the lung, they are prone or they are subject to dynamic differences. So they are transported to the lymphatics and to lymph nodes and so on and so on. There is clearance and everything. All these things which are very hard to mirror in an in vitro approach. How is that considered? I don't know, it's hard, it's complex, but this is what puzzles me, really.
Yeah, okay. I will start with cell selection because this one is pretty simple. You can actually use any kind of cell which would quickly express the responses which you based your prediction on. So basically, we tried many combinations. It's just different sensitivity of the experiment. So the trick is in validation. So you can use whatever tool if you can derive the same result against you calibrate or validate your model. So basically, how we perform usually is we take those cells that express this functional response as fast as possible, and not only cell, its entire cell system. So some of the events are material specific or disease specific, outcome key event specific, and many of them are not. Yeah, so it's about cell selection. It's a complex question. I can even tell you that we mixed human and animal cell data, and it's a funny system, and sometimes it's even increasing the sensitivity of the model, because it's basically those subcellular events are not cell type or even species specific. They are the same. They are driven by physical interactions. That's why there is no need to worry so much about the cell types. About the dose, yeah, it's a long expertise which we gained through different interaction, different consortia. We primarily use surface dose, surface to surface. So surface of material against surface of a cell. So that's our metrics, because it's known that the cell response, the cell is the most sensitive machine in the range somewhere around close to unity, 1-to-1 surface dose. With respect to higher or lower doses, that's usually you refer for the mass dose or surface dose per volume of your cellular sample, but that's not what it interacts. What interacts is this small particle surface that is really close to the cell. And we are measuring these doses directly from the experiments, and I can tell you this is much less than 1% of the dose, which you deliver even in vitro, and it's pretty very much the same like a dose which you calculate from instillation experiment or in inhalation experiment in mice. And then the third question about the dynamics and the clearance. What we claim is that we will provide a description of an effect for what is inhalable fraction, so what reach the alveolar part of the lung, so alveolar epithelium. Yeah, we are sure that that part of the dose is never reaches the alveolar epithelium. It's cleared before, so it's primarily bigger part of the size distribution. Yeah, we even tried to use Ali interface with dynamics, and then we figure out that it just time modulation of the dose. How fast did the dose reach the cellular after the surfactant layer? Mostly is few hours delay. So it's yeah, it's a big question. It just, we always come back to the point we want to solve. We want to get prediction with the least complex and the most simplest case, which is still complex, but the simplest one.
Janez, thank you very much. Thanks. Keep the questions if there are any left for the discussion. Now we move on. It is Roland Grafström with us, and he will tell us about OMICs, the application of OMICs for the regulation of materials. So Roland, you were waiting along, so now the stage is yours.
Certainly. It says someone else is sharing, so I can't share before the other person stops sharing. And when the other person stops sharing, I can share.
Janez, could you please stop sharing?
Janez, can you stop sharing, please?
I can do okay, but can I do okay? Okay. Now someone else is sharing is what it says.
Trying to.
Yeah, Janez is still sharing. I just asked him to stop sharing.
Okay. So
wait. Can you just kick me down?
I kicked you out. I'm sorry. I hope that was okay. I think Roland should be able to share now.
Yes. That looks better. Yeah, good. Very good. No, it should be. It's not starting from scratch. Sorry. Gotta go back.
No problem. We have time. Just take your time.
So here.
No problem at all. Thanks. Now everything is okay.
I think it's working quite well. Yeah. All right. I'm coming out of a cold, so I'm standing up because it helps my voice and hopefully so. So I'd be delighted to and thank you for the invitation. And I'm Roland Grafström. For those of you who don't know me, and Pekka and Penny, we've together put this presentation together for you. We work at the Institute of Environmental Medicine, and the first slide actually relates quite exactly to what the Institute has the instruction to cover. And that is that, of course, we are at Karolinska Institute, where the academic investigator view is very important and central. But we also have the mandate to develop tests to be applicable. And we also have the mandate to support the regulators. And if I then would make it simple, I would say that Pekka maybe stands on top, me in the middle, and Penny now with her recent roles can see the regulator. But I think that had helped us a lot in putting this together, and also relates to the presentation. So just to go very quickly, the academic investigator, of course, has some specific interest and goes and likes to have scientific novelty and plausible mechanisms. And the developer goes also with a particular model, and it relates to the discussion we had yesterday and just recently from Janez's nice presentation, and likes to have a robust and relevant test where the regulator, of course, all the way goes to productivity. But I will tell you today about tools and ideas so that which covers these three areas. And a very important point for the two things is that we need to build on what was discussed yesterday quite a lot: the mutual acceptance of data, the MAD, and also the legal certainty. So the two things really to take-home message that I cover, one is about the OORF, which is the OECD OMICs reporting framework, which will be very important for regulatory applicability of OMICs. And the other thing is a tool, which is we term PTGS, which stands for Predictive Toxicology Space. And I think all of that together will share for you how what is on this slide actually is important to land in something trustworthy in the end. So this paper, Toxiconomics, a vision for the 2020, came a couple of years ago, and Pekka found it first and came to me and said, well, I think we actually look at all of these things, we consider these things. And I think that relates exactly to my starting point already. So if we go from the bottom, study design, technology, gene activities, mechanism, predictive models, and decision making, which of course in the end is very much coupled to harmonization and standardization. Then we can say, what is the future of the study design? How can the technology evolve? How is it reliable, reproducible? How should we present data, and which data should we consider? Now, if I look to the work that we've tried to do, and I see that is very active over the 25 most recent years of active exploration of omics, it goes very much from nanotechnology, having very competent cells, whereas induced pluripotent stem cell version, more simplistic model to more complex models, so on. They also goes from a variety of technologies. Now we are more left the microarrays behind, and we are on to RNA sequencing, which I'll come to a little bit. We integrate our various thinking into AdMas, and we certainly look also beyond mRNA. Now we go to the activities. We maybe started off with genes, individual genes. We now are much more in the omics, into gene sets and signatures, and overall looking to networks and functional models. And the technology that we use to analyze omics relates to what you already heard quite a bit on in the workshop, going to mode-of-action, adverse outcome pathway, anchoring our results into the AUP framework, using AI-derived technologies like machine learning, trying also to find low doses, where do we see lowels and nowels, and also use it for read across and grouping. And certainly here again is the mechanistic information and predictive results. And I can't any longer see this text, but maybe I can take away this box here. Yeah, there. So this again is very important on things which are in this framework, the omics framework, standardization, finding confidence in data, and having transparency on how you report these things. Anyway, this study was setting the scene a lot, and I think it's been very influential on the thinking of omics in the last couple of years. Let me see now, how do I change it? Here, yeah. So the example that we decided, the three of us, to take and discuss a bit more, we certainly do the things that Janez discussed. We do put it into the AUPs and so on. But I felt grouping and also Penny and Pekka to represent a very important one, where we can get the regulators who particularly interested in the application of omics data. And from this, a very nice recent article from Mark Wyant. Here is a very simple scheme on how you can conceptually do this. You identify an endpoint to predict. You find some chemicals or materials in this case, which is the topic, of course, now today, to see if they are quite similar. Then you design a study, you generate the omics data, and you measure bioactivity. Bioactivity in a broad sense, like Janez reported, or many other ways I'll show you in a moment. And you consider all these data useful for grouping. And then you make some interpretation, of course, of this, define the group, and you can move from the grouping to read across and predict toxicity to fill data gaps. And there we believe that, and I think many with us, that getting the regulators community on board would maybe be a top thing to consider for the omics. However, very important is this aspect of bioactivity similarity. That's maybe a take-home word to use and to consider in the context of omics, but also to realize that this sounds all very nice and simple, but most grouping dossiers still fail. And maybe partly because they have not used omics in very specific ways, among not defining many other things. So let me then tell you about this tool that we started to do actually 15 years ago, considering AI concepts before AI concept was termed AI concepts, but certainly machine learning, which is capable of analyzing many aspects related to hazard, mode of action, and grouping them. We'll try to maybe give a bit more data on that today, as well as potency. And by combining large data and using machine learning, in this case, the connectivity map, and also the NCI 60 data set on toxicity effects of thousands of chemicals, and combining that data, and first of all, compressing the connectivity map to 100 components by machine learning technology, then we would find that 14 of those components were directly coupled to toxicity effects. And that set then this space, this toxiconomic space, contained 1,331 genes, and we subsequently developed a complete tool on that basis, having a lot of data collections in our hand and being able, with diverse methodological bioinformatic techniques, to relate to that. And I'll show you very briefly on some materials data how we can predict cytotoxicity on that, how we can define lowers, how we can do mode-of-action analysis on a component level, how we can use that for grouping a little bit, and how we can map it a little bit to AOP. It will be very superficial in this short time, but anyway, gives you at least a hint of how we work. And a very important part here is that the scoring, as we have developed it, considering also the regulatory perspective, really covers a very important aspect of applicability, relevance, reliability, prediction, and also defining applicability domains. And we believe them, of course, to be very relevant for what I started off with discussing, the perspectives. So what are these components covering? Well, they're covering, these are the 14 components here, and they do cover a lot of toxicity associated biological and cellular mechanism. They are clustered from overlap from gene bases in a couple of clusters and individual components. And here's a lot of stress signaling here, a lot of cell cycle here, and many other things. And you have to go to the paper for details. But anyway, that is a basis for a quite easy grouping, in fact. If you analyze it, these component pattern, and you can compare it, and 14 components are actually just very few, and you learn very quickly to deal with them. So here's an example of a study by Tilton et al. Some years ago on carbon nanotubes and nanobelts. And here is a first derivation of Lowell. And the point we take is to first compare the control versus the exposed, of course, and see that it's significantly different based on gene set enrichment analysis. And the second part is that it has to pass a threshold in relation to a reference data set, in this case, the connectivity map. And you can see that in this case, the carbon nanotube low concentration is doing that. You see increased gene expression here, differentially expressed genes. And you can also see that the lowest concentration of the nanobelt also did that. Now you can analyze this on a component level by looking at the enrichment of the 14 versus the other 86. And then you can see that the low dose have certain components here. A means very high toxicity, and then you go down in low toxicity. So it's a mix here. And if you go up in dose, of course, you have a lot more. So let's go just to the next one, just to indicate to you how we also analyze it in relation to the AOP networks. So here are this study on top, just to show you. And here are lines. This is a so-called eye diagram. And the lines get thicker if you have a high response. And you can see, of course, that you have a higher response to more components, where you would see lines to, in this case, the C and to the F here, the C and the F. And you can see that that's higher. And then this is now reflected on what we term the PTGS AOP ohm. So 25 lung AOPs connect variably to these 10 different materials from these 6 studies in human lung cells. And that shows you the complexity of the analysis. Relates also a little bit to the previous talk, that all these key events are very much shared among these AOPs, and therefore you see this very typical, very broad responsiveness and network character when you truly in depth analyze the data based on the PTGS algorithm. Now, this eye diagram, anyway, also to say typify what is termed explainable AI. Maybe that's something one can come back to. When you have effects, you go via a standard and you do it. So you can visualize three different things in parallel and exemplifies an explainable AI. Now, I can also use the groups, AUPs by grouping, and this is exactly the same data here. And you can see that we based on the AUP pattern that comes out for each of the 10 materials, we can group them here. And then we can also see that there's a various doses of 10 materials. That's why it looks like a lot more than we have 3. And you can see that the enrichment and significance level for AUP varies between the different clusters. And this middle cluster here has a lot lower expression of AUPs via the PDGS system. So we have then, let me get back a little bit to the general and then end up again with the PDGS. And maybe just take a couple of more minutes. So this is something which is really ongoing and developing, and there is action to formalize this thing, which is really good and very timely. And the whole idea with this, and here's a reference for you on this, is to really promote these sentences that we had already on the first couple of slides, the transparency and support standardization, and the fact that there's regulatory relevance that can be reproduced, really producing confidence. It's not a test guideline, OECD, and it's not a prescriptive stipulation of analysis. Actually, the idea here is to have something which is really flexible, but still very useful from the regulatory perspective. Going back a step, if you think generally on omics and the fact that bioinformatics workflow have always been described for omics, they actually align with this ORF, the reporting framework. We have good databases for omics data, and we also have pipelines for doing the experiments, all the way from looking at many chemicals, chemical space, considering groups, etc., experiments, and pre-processing, reducing the data, collapsing the data, looking at various level of analysis, and doing prediction and mechanistic analysis, and in the end, bioactivity-based interpretation. So it follows a very modular structure here, the reporting frame, and from our view, we also see that PDGS follows this. So here are then you have to go to the paper to go to detail here, but there are then instructions how you can do this, how you report, how you do the toxicology experiments, and if you then go on the omics analysis level, there's of course differences between different type of technologies. This also includes metabolomics here, this publication. But here, this is certainly something that we do exactly, and which was also covered on that previous slide on the predictive toxicology space, pathway enrichment analysis, looking at differentially expressed genes, doing benchmark modeling, which I didn't talk about, but typically grouping and the PCA analysis is an example of the multivariate analysis that you do. The FAIR principle then is of course very important. We heard about it yesterday a lot, and we also heard it a bit brief today. And I'm not going to go in deep depth here. I think you all know what this acronym stands for. But a very important other part of it is taking it to the next level, and this is certainly key for omics analysis, is making the data machine actionable. And that actually relates to the other variant of the FAIR, findable AI ready, which you may have seen in a publication that came 2022 in Nature on material science. And that is also something very good. And for those of you with Penny being senior author here, there's a couple of papers in Nature Nanotechnology and Nano Today, which deals with these things. So there I refer you to those. Okay, going back to the PDGS and summarizing then, We really believe in agree with broad applicability of it. The way we constructed it, consider the academic test development and the regulatory concept. So it serves actually as a giant grouping and AUP applicable toxicity biomarker. And I'll be glad to discuss that a lot more when it comes to toxic dynamics, etc. Some of the questions that came up to the previous speaker. And it captures and describes dose response and toxic mode of action. We can apply it in high throughput manner to diverse data set. The initial selection of toxicity-related genes cover multiple pathway, and the good thing, we avoid unspecific gene expression noise. We really have a standardized, very much data-driven principle here. We consider completeness and quality naturally, and take absolutely very important is that we don't do arbitrary differential gene expression cutoff. They're totally eliminated. All gene expression level is considered. So we believe that we have doing something which follows the FAIR principle in being both reliable, transparent, and machine actionable and AI ready in that way. And very importantly, here we have a chance, something that was also discussed with the previous for the previous presentation, to go very, very sensitively, very low. The fact that we have a whole genomic space which cover possibly a majority of toxicological reactions makes it very, very sensitive, often 1 or 2 orders of magnitude more sensitive than standard cytotox test in cell lines. So overall, here is a slide that I actually made yesterday, and I know Penny and Pekka has not seen it, but it was based on the discussion yesterday. And I thought that it would be good to reflect on that because there are many things coming up in terms of cost and applicability and AUPs and so forth. So here we do have an OMICs generally, not only PDGS, but OMICs generally. We can go from many data points, results at the single gene level. We can convert that to fewer data point outcomes and interpretations. And we can use it all the way to yes or no predictions by having thresholds and reference data sets. And I think we believe, Pekka, Penny, and I, that can you have a better way today on the basis also of the costs coming down to do predictive studies? I can't think of any better way, but I'm of course totally biased. Yeah. So cost for a transcriptome analysis, it also came up cost levels is 1,000-fold lower since I started work on microarrays 1999. So that is the 25 years from around 20 kilo euro per microarray to around now 20 euro per sample for an RNA sequencing analysis as an informative read level. The regulatory relevant outputs are many. They relate overall broadly to hazard assessment and accordingly also to risk assessment, naturally, as hazard is a part of risk assessment, mode of action, grouping, and point of departure, which I only touched very little on this time. The anchoring of gene expression to the AUP framework. We heard a super presentation in my mind from the previous speaker. We also do a lot, and it's possible actually both qualitative and quantitative ways. And also relating to the discussion yesterday, considering from 1 to all the key events. So you can score, you can translate the AUP analysis in vitro. And in this context, I actually like the term that Elizabeth Berggren used yesterday, reverse engineering. We use the term reverse translation very often in this case, where we go from the in vitro analysis, the noun-based studies, and try to translate, as heard in the previous talk, the inflammation. We do it also on typically fibrosis, cancer, besides inflammation, and maybe some other time you have opportunity to hear that part of our work. And PDGS then exemplifies methodology developed specifically for AUP-coupled hazard risk assessment under the concept of utilizing big data and artificial intelligence. And we do stand very strongly now, the 3 of us behind this presentation, that it's very timely to formalize the OECD OMICs reporting framework, considering that this OMICs field is very mature. extensive utilization, exploration, standardization have been ongoing on. And I mentioned transcriptomics, but it certainly spills off also to other types of omics technologies. Finally, this is maybe an odd way to refer to the many projects that supported our work, but omics, but it also gives me a chance when it's structured this way. This is the final slide. That is that the omics, of course, is placed very centrally in the way we do NAM-based risk assessment. And I've shown particularly here the material focused projects and where they are, all the way from actually in the current harmless project, where we try also to use the PUDs and convert them to exposure assessment, so that we're not only doing hazard, but also moving in a little bit to the overall risk assessment. We combine the omics normally with the high throughput screening approach, a little bit like you heard from the previous presentation. We certainly have the PDGS scoring concept and omics in the middle with the dose response assessment. We develop further now, for example, also in the PINK project, where organizers of this workshop also have a big interest and involvement in computational models and benchmark dosing and so forth. We also do these kind of extrapolations, which I didn't mention a lot this time, and very much so at a low toxicity levels. We think that this complete variant of high throughput PDGS and AUP can take us very far. And I'll stop there, and I'll thank you very much for your attention and being there today.
Thank you. Thank you very much for a very interesting presentation. Are there any questions? Are there any questions? No, then I take a second. I have one question. There are already a lot of data out there, but probably not all the available data is somehow accessible or in a format to be reused. How to handle these existing data, or there are new methods on the horizon who will do it in a more simple way and still get all what we need?
Yeah, I think all of us, Penny and Pekka and I, often give presentations where we also refer to the many databases and store data. And I didn't go very in depth there. I should have probably mentioned, but I wanted to keep reasonably in time, the eNanoMapper database, and where we were also part of that project, the eNanoMapper project, and that database where all these making data machine actionable. We're doing a lot of efforts there with those persons who run that database. So I think there's big awareness of that. The high throughput, for example, data, it usually took a month to analyze to two. When you do something like 150,000 data points, that is now down to 3 minutes. So I mean, we are moving, and so is the whole field. And I think Thomas will, who I see him coming up there on the screen, he will be the next speaker. He says actually has that topic. So I think there, but there is a lot out there, and it's again this idea that I mentioned. We have the PDGS there in the middle, but we also couple it, thanks to Pekka's fantastic bioinformatics expertise, all these other data sets. So they are at our hand, at the tip of the hand, and you can very quickly analyze in relation to existing data. So I think we actually, I see that we have enough to do, let's put it that way, with accessible data. And are working on doing even better job. So yes,
perfect.
Thanks for the
Now
question.
Thomas will tell us how to do it. Yes, how to organize, manage, and all the rest related with the data. Thomas Exner, now the stage is yours to tell us what to do and how to handle metadata in particular. Thanks.
Okay, thanks a lot. I hope you can hear me. I had a little bit hard time to find a quiet place because I'm here in a conference again. Yes, I now will follow up, and I think I also have the last talk in this workshop, which is always hard to be, but I think it gives me also a chance to recapitulate a little bit the day, because with Anna's talk at the beginning, you will see that there is a lot of overlap in the first part, but then also definitely going into what Roland just mentioned with FAIR and how we get data and how complicated it is to get the data. So you, Damiana, we talk a lot about this problem. Yeah, and starting with that all is that we need to think about what are the challenges. Yeah, and I think the availability is always a big issue. Yeah, that we have too little data. Everyone is complaining about data availability, but in principle also, which is combined to that, understandability. Yeah, you need to understand what, if you want to use other people's data, you have to be able to understand what they have done. Yeah, and this is then going into the area of reproducibility, repeatability. Repeatability is really, you do exactly the same. Reproducibility is more you do something which is then more getting you to the same output or outcome. Yeah, that these are, you can do it slightly different, but you still get to the basic chemical, physical, biological, toxicology outcome in the end. And having that is just, again, these FAIR principles, which give us a huge set of statements which we should follow to become that. Yeah, and this is the problem with FAIR, and I will not talk much about FAIR, but they are really principles. Yeah, they are not hands-on sessions or lectures on how to do something. Yeah, they just say, what should we do? The next thing, and this is then becoming more into the also regulatory, but also the AI area, is trustworthiness. Yeah, we need to understand the data to be then able to say, yes, we trust that outcome and we want to input that. Roland already mentioned relevance. Yeah, to really say, yes, this is good data. We understand from how it is presented that it is high quality data and it is also relevant for us. And there is a couple of other principles which are less often used, but I like the trust principles because they really give this focus on, yes, there is open data, but if you don't understand them, we cannot trust them, and then we will not use them. Yeah, even if they are there, if you don't trust them, you don't use them. And in principle, I just use this garbage in, garbage out to say, we often just don't know if you use or what that is. Yeah, and then we always go back to that. Yes, we know when we put garbage in that we get garbage out. Therefore, I don't know if that is okay or not, if I can trust this thing. Therefore, I keep away from data. Yeah, therefore, we also don't use the existing data as much as we can. Yeah, and for really thinking about how to get to this stage, to not only have data available, but to have usable data available. There is this idea of data documentation. I will go into detail what that means, and provenance, that we know where it comes from. And I like this picture here on the right because it really shows, even if you think that at one point of time everything will be done by AI, AI has to be based on something, and this is data. Therefore, we have to still think about how we treat our data, because if we just put them in a bad shape, the AI will use this bad shape to train itself. And this is going back to Anna's first talk today. In principle, we are now looking at materials which are very, very complex, and we look into status of these materials in complex matrices and in products in the biological system and so on in the environment. Therefore, there is a lot we have to cover, and this makes data coverage and data collection so complicated. And this, just to go back to Macrame, to just as an example, all the other projects are using very similar case studies. We have a lot of different areas, different materials here on the left. We do a lot with them, and have a lot of different new and existing methods. Some of them are already test guidance and so on and so on. But we also look at different stages in the life cycle. there was a very nice, very interesting talk about question about mining. Yeah, really looking at the raw materials, but that is one stage, and then we go on to the production, to the pristine material, and then to the product, and then to end of life. And all these things are very important, and we have to cover them, and we have to describe them in the data itself. Yeah, and this is just this very complex thing we started with in the macrame to define which are these sample points. Yeah, what do we want to look at? Yeah, the pristine materials, then also incinerated, abbreviated materials. And you have to describe them. Yeah, it's really a question of how much can we actually describe them? How much do we know what that is? And perhaps, especially at the beginning, we know, okay, this is a material in a matrix, but we don't really know what happened to the material, but we can explain what happened, not how that looks or how they changed the material itself. This we have to analyze and to characterize. But in principle, we also know what happened as a history to this material. Yeah, and therefore there are two different ways to describe materials. The one is, yes, we characterize it 100% fully. And then the other one, we just look that we understand how it was produced, what the steps were until the step we are really looking at, the stage where we are looking at. And this is what, yeah, just as one question, yeah, what are we really looking at when we have a water filter which we incinerated and there is graphene oxide in there? Yeah, at the beginning there was graphene oxide in there. What is the thing we are looking at? And for doing that, we had these instance maps, which are really a nice idea to follow different steps to say, okay, you have starting materials here, you then go through the process to build the nanoparticles. Then these nanoparticles are somewhere used, and then they go into the end of life stage. Yeah, and we can follow that, and by visualizing, but then also by putting data behind that, we can actually have another description of that material at that stage actually is. Not a chemical description, but a more fate history kind of description. Yeah, and in principle, you can then do very many things with that. Yeah, you can look at going back these instance map and say, where is this material is coming from? But also, where is the data coming? Yeah, therefore, there is a lot of different provenance. You created samples, what happened with the samples, what happened with the material itself, and so on. And therefore, you have this going back and understanding what that thing is. And if you then do make a measurement on top of that, you can say, yes, this is exactly the same stage. Therefore, we can compare it. Or this is a previous stage, and then you have to decide if these two material or these two data points are describing the same thing and therefore can be combined with each other. Yeah, this is just, I can go through that. This is just to show that there are these different steps. You have the starting materials where you look at, some of them have real measurements behind them, here as well. Then you have the production, and then at the end you have the final pristine material, which you then also combined, but in principle, the final state is described by all these information, also information on the raw material. You can also assign responsibilities to that. And I think this is also when we now go into these very complex advanced materials, it's important that we, and especially life cycle, we need to know everything about the raw material, how they were extracted and so on. But you can now push that to the raw material providers. They are responsible for the characterization of the raw materials on describing the part of the life cycle assessment, which is relevant for these raw materials. And then this information can be given to the downstream partners, and they then add information on the production and on all the other steps, the use and so on, and the end of life at the end. The other thing is, how do we get the data? And I think the main point here is always that it is, yes, we have to document a lot of things, and provide information that we can really understand what the data is. Therefore, we have to make it as easy for everyone to do so. And I think this is what we are struggling with, because all these templates and so on are very complex. The other point which I see as a problem, and there it's nice to have as a topic AI and regulation at the same time, because you have different users, and the different users need the same data in different formats. Format in a way that not only this is Excel or whatever, but in principle, what do we have? And on the left side, you see this kind more a modeler view wants to have a lot of information from many materials for one specific endpoint, while the regulator, the risk assessor, is more interested in, oh, I have this molecule, this material, this nanomaterial, I want to know as much as possible about it. And this is different. These are different data and databases which are behind that. But it makes it complicated to get the one data, the same piece of information from one database to the next. And then there's the generator. A data generator, you are using lab notebooks, you use Excel. You don't use data formats in the form how they are how they are stored on databases. Therefore, also they have their very idea. They want to use the same workflows in different projects, and then they have to put that into the one format from macrame and the other template from, I don't know, eye care. And even if it's the same data, it might look very, very different. And a person in the lab to do something, one thing, and not do some different things for the same data, depending on which project this is made for. Therefore, we need something where we have at the moment this stage where everyone, the data producer, are generating data all over the place, and then they have to transform it for the data users. We need something where we do that once. The data generator is putting that in, and then there is magic happening, and hopefully this is the computer which is then doing some magic, and then this is going back to the format which then either the modeler or the risk assessor or somebody else downstream can use. There are ways to do so. This doesn't work so much, but in principle, there's a lot of work on these kinds of how can we make that work. Then all the ideas of ontologies come in and all these things, because we have to put these things into each other. But the main idea is that we have one data schema which describes a set of data, and we can transfer that into another data schema, which is then used by somebody else. And this has to be done automatically, because otherwise it doesn't scale. It will always be the bottleneck is putting the data in. It has to come from what you in the lab produce, and this has then magically go into something somebody else is using, because otherwise, as I said, you just have this bottleneck over and over again. For that, we need some kind of definition. These data schema have to be standardized in a way. Not completely, not every single field, but at least that you say, okay, if I have a step in a protocol, they use a little bit similar ideas of how the step is presented, but in the same way, everything else. How do we present materials, for example? These kind of things, that we just go into these small steps and say, can we get that to something where we can agree on a small level, not on the full database, data set level, but on small pieces, can we agree on that we always describe an instrument by these attributes, and others can add things, but at least these things will be there, and then you can transform that from one data model into another. Just a couple of examples. The best way is then to have that stored, that other people can reuse these prototypes, these of data models. And this is now why the color code in the background changes, because we move from macrame into the pink project Roland already mentioned, because there we really want to go into this infrastructure behind that we can say, okay, these are different data models. These are versions of data models. These are somehow mother-daughter relationship between data models and so on. Yeah, and in that way, we hope that we use these data models, yeah, or at least part of these data models we are creating. And at the end, I don't want to go into the idea or into the whole thing, but the idea is really that every single data set is more or less explaining itself. It's not a part of a database anymore, but each data set is self-containing in a way that it describes itself, how it is structured, and how this data model is created. And in that way, you can integrate that in different databases, one for the regulator, one for the modeler, or into different platforms, risk assessment, decision support platforms, and so on. And for doing that, you need the infrastructure, which I think is starting to build, but it's clear that this needs to be something which we generally agree and generally use. And this is just to say, okay, there is this transition from something which we do at the moment in macrame, yeah, where we have this system already established in a way that we can get data from data producers and put that then in a more harmonized data format. But in principle, we want to go further, that this is something which is not project specific, but can be based on a global infrastructure, which is exactly providing these kind of interoperability, findability, and these kind of tools, which can then help you to get to the information in the format you want to have. That's all. Again, we are now in the pink color, coming from the magenta from macrame. But I hope that we can continue on that, and in that way really also structure this standardization and hopefully also provide data then for all the regulatory evaluation and OECD guidance development. Thanks.
Thank you very much, Thomas. Thanks a lot. Time for questions.
I think there is a question on the chat, Damiana.
Yes. How does your work link with effort on metadata characterization, template standardization, like CHADA that is currently under revision?
Yeah. In principle, it always comes to the same thing, CHADA and MODA and any other QMRF. I think it is important to follow to have these standards, and we are following them very, very closely. For me, the main point there is more what do you have to cover, yeah, and this is what CHADA is at the moment creating, that we have a set of or that we just know what kind of metadata you have to provide for a specific area. I would always like to separate that a little bit from the technology behind that. Yeah, CHADA was, I think it's still, I'm not sure, but I think it was for a long time just a Word document, which is absolutely fine. Yeah, but in principle, there are the two steps. On the one side, you have to define these data models, which I was talking about, and this is what CHADA is doing. Yeah, they define a data model. And then there is this infrastructure around that, which is building, indexing these data models, comparing, and also then covers, for example, updates and changes and perhaps modification, which are needed then for specific things. Yeah, therefore, there is a lot of overlap of what we are doing, but I still would like to separate this kind of idea that CHADA, QMRF, and also the OECD harmonized templates and many others and templates we used in the different projects. I would really like to keep them as something which is, they define what we want to describe, yeah, and then we can see how we want to describe that. And this is a second step. And what I presented here was, on the one side, that we can transfer between data models, but in principle, the easier thing, we can also transform between different data formats in a way that we can use. I showed a little bit of JSON there, we can create from an Excel sheet a JSON, because JSON is something computer modelers like more than an Excel sheet. Yeah, therefore there is always this technical details, but this is the simpler thing.
Thomas, can you go back to the previous slide?
Yeah, previous.
Oh, no, or just leave it as it is. Sorry. I see a hand of Blanca. Blanca, go on.
Yes, so listening now to Elise and Thomas, something came to my mind. I see all these projects, and many of us are, or many people are in the projects always, and I feel sometimes we are just talking to ourselves. And I know that there are also some efforts outside this bubble, but they are private databases. And I'm wondering, Thomas, if it's easy to reach out to those guys, because we are all comfortable talking to ourselves. We know about all these different templates. I think you are trying to also get ontologies, so data from one template can be maybe translated to I don't know. But how about all these other efforts, which are kind of private? I suppose that we have to pay to get there. Would you also think about exploring outside of this EU project bubble? Maybe we can learn more, or I don't know. We already have enough with all these projects anyway, so we are already busy enough.
In principle, the idea is that this becomes general, and I didn't talk about this data documentation part so much, but in principle, what that means is that each database to be interoperable. Yeah, there doesn't mean open, even if many, me included, would like to have as much open data as possible. But in principle, there is no problem to have closed data. But you need to understand how you can use that. Yeah, and this is what this data documentation is. We describe how these data sets look like, that other people can, in principle, without seeing any data point, they can write converters from one data set, from one database to another database. And this picture, I just put that up again, because in principle, that can be on a database level and a data set level. Yeah, data set level, because then we also can give access rights for data sets and not databases. Yeah, then when you, Blanca or Damiana, you are producing data, you are in charge and you can decide to whom you want to share that. But for doing that, every data set has to be described. It has to describe itself in a way that then people can build these platform databases on top of that. And in principle, databases are then becoming more as a visualization tool. Yeah, they are not more. They store data, yes, but in principle, their main purpose is providing functionality to analyze the data, visualize the data, and so on. But many and very specific to different ideas of what people want to do with the data. And for me, it's clear that databases have to be very specific for one purpose. Yeah, this is what I presented with the AI or modeler versus risk assessor idea. But they are also very easily outdated, yeah, because technology moves on. Yeah, therefore we have a lot of data in databases, but in principle we would need to take them out and get them into the new databases. And just something which is a nice story, because I looked at one point of time in the G Gates data set, and Roland knows that very, very well. And I looked in which databases it was in there, and I found the same data in every single of the data of the EU project we were in. They all integrated the data into their database. Yeah, because yes, it was, if you do a new database, you have a very specific kind of idea on how that looks like, and therefore you have to transform every single data point again and again and again. And I hope that this will help. But we need, for doing that, and back to your question, we need for that the full support also from the commercial database providers.
Thank you, Thomas.
Thank you.
Thanks a lot. Any
Long.
other questions? We entered the afternoon discussion, so the questions could be also for other speakers of the afternoon, not just for data and Thomas, the last one. Any other questions? Any other questions? I don't see other questions. Okay. then I do have two questions, and I hope they are also relevant for others. You and some others are keeping saying that we have to provide as detailed description of our data set as possible, so that we need to provide as many metadata as possible. But it happens very often that we don't really know what metadata are relevant, because very often some things for us doing experimental work are so, let's say, either are not something that might be relevant. They're something what is we are doing or on the everyday basis, and we just are not aware that this might be relevant for the future use of our data. Yes. And we also know that we do have existing ontologies and so on and so on. But for us, data providers, this is another field. Bioinformatics is not something what we are familiar with. How to bridge this gap, that we know how to do, why to do, and you help us to really be familiar and skilled to do this task.
Two answers. The one is that what we try, and this is what data provenance for me also means. Yeah, the things are that putting all the things you are normally documenting into a database, as you said, makes probably no sense, yeah, because you don't know if that is relevant at all, and it takes time to do so. Yeah, therefore, what we try to do with this data provenance is that you can actually go back, yeah, that you have a database entry, but you can then go back to the original file. The database entry will not cover everything. Yeah, but because you can go back, you can see, is there anything? I now find some new things which I cannot explain. Yeah, therefore I would go back to the original data and see, is there anything in there which, for example, could lead to differences in the outcome? Yeah, that you say, okay, perhaps it's a different batch you use for the two experiments or something like that, which batches are for me something we should report. Yeah, but just as an example, yeah, that you say, okay, I have twice the same nanomaterial, I do the same experiment twice, I should get exactly the same result, I don't get them. Why? Oh, because they are different batches, and there might be something because these different batches might differ. We don't know why or how, but we know now that they differ. Yeah, these kind of things. That is the one. The other thing is that I hope that we can learn from each other. Yeah, that these kind of ideas, that we have these data schemas defined, you will see, because we also learn. Yeah, we have also not the answer what metadata is available, but you can then learn, oh, this person doing the same experiment decided that this type of this metadata point is important and he wants to report, she wants to report it. Yeah, and then you can go back and say, yes, in principle, it might be very relevant. Perhaps I should also document that. Yeah, and in that way, we don't sit down now and say, okay, this is the metadata we cover. I know that this is very different to what regulators would like to see, yeah, but I'm coming more from this. We start from science and then we go into something which is very well defined. Yeah, but we need to be open to this. We still have to learn, and we can learn by people who do that on a daily basis and say, okay, but for me, it was very that I cover whatever the moon phase when I did my experiment. Yeah, stupid example, but yeah, but these kind of things. Yeah, that we learn from each other, and I think this is the important. There is that we start thinking first about data schema. What do we want to describe? Because when you compare Excel sheets from different people, they look completely different. Yeah, same experiment, two people in the same lab, they will use very different Excel sheets, but they probably still have a very similar idea of the data which has to be covered in their head. And therefore, we should go back to that and discuss these things and then say, okay, then we make a template out of that at the end. But that is the last step.
Thank you, Thomas, very much. Thanks.
Sorry, I talked too much, I know.
Absolutely, no, absolutely perfect. And now I ask similar thing to our previous speakers, Asmus, Dan, Janez, and Roland. What do you think about data reporting and verification of images and what metadata to report. So how do you handle this? How do you approach it? So if I ask first Asmus as our first speaker of this morning, how you handle this reporting of your data?
Yeah, I advocated using the Nexus data scheme, which is being defined or reworked by the FAIR-MAT consortium. And this is an HDF5-based binary format, which holds many slots for metadata that were defined by experts in the field. So for every microscopic or analytic technique, there's a Nexus data format. And there the experts have defined what metadata is to be stored, maybe stored. So you must not fill in every slot, but you get an idea what data might be relevant. For instance, if you're doing Raman spectroscopy, there's a slot for polarizers being used. So you might not have thought of whether polarized signal analysis might be relevant in your field, but there's a slot that reminds you to think about whether you should provide this data feed. And there are base classes that define also the experimental setup, and you can, and the individual instrument formats build up on these base classes. So there's a real hierarchy of data formats and pockets for metadata that helps you to cover all necessary information and to provide it. And this is something I really like. So it's a family of formats.
Perfect. Don, what are your experiences in your institution?
I have started to chat with Asmus in the chat. They are also, or I'm also active at the ISO level. Therefore, some questions from time to time from my side. For example, EDX, the spectroscopy, is already standardized, or the format of a file of a spectrum is standardized since 20 years, and it works very good. It is a vector at the end. It is interchangeable. It comes from the US as several other standards, and there are many, many years of development. Also interesting. And one point that is important at this stage is that in this standards, this is just one example where the standardization of the data, of the formats, metadata is working. The microscopy is coming. We need the instrument manufacturers, all of them. And for EDX, for electron microscopy, all these manufacturers are in these technical committees and parts of the development of the standards. I think it is very important to take them or to work together, but in any case, with the instrument manufacturers. The next standard is a very simple title, TIFF for SEM. Again, it is not very new, but after many, many years, it's well defined, and you have a very, very long list at the end with all defined instrumental parameters. Too many, probably, for most of us. We can pick up only the most important ones, but the key words, the terms are defined already, agreed after many, many years. This would be my message maybe at this place, not to duplicate or to start again what already it has been done by some communities, including instrument manufacturers, and after so many years. And the next standard I can call is the so-called hyperspectral file format, coming now from 2D to 3D and being open to more methods than microscopy, also Raman, for example, or yields or whatever. It is a very fresh standard, ISO at ISO level, coming again from developments from the US and being adopted almost one-to-one. So staying all together, and also ISO with OECD, also at European level, the resources, all of us, are so valuable not to restart or to do parallel works, for example.
Thanks, Don. Janez, what are your experiences with metadata selection and then description?
Well, we have tried, Roland will remember that we have tried in Smart Nanotalks trying to insert this metadata from live microscopy. We worked with Penny for quite some time. Well, at the end, I'm still quite skeptical. It's there's so many experimental tricks that somehow should be annotated, but they're not, and they're not reported because there are too many of them. So I think it's primarily the one who do the experiment should make a resume out of the experiment. And if the experiment is meant to be used elsewhere, then, well, the one that make a call for such experiment should define what kind of metadata should be included. For example, I can give you a very simple experiment, a very simple example. If you use in fluorescence microscopy, we always use probes, but it's super tricky what kind of concentration of probe you use. If you, for example, you label actin, if you label it at very small concentrations, then the actin dynamics is almost preserved. If you increase the concentration too much, then the actin dynamics is hindered, which completely different entire story. The images looks the same, but the dynamics is poor. So this is just one tiny example of how very important is that you actually should report everything, but in principle, this is almost impossible. So the one that interprets the results, the first that is responsible to deliver what is needed to be delivered. Otherwise, I'm a bit skeptical that the metadata are enough.
Very good point, Janez. Very good point, and very good point also because you nicely distinguished on one side, as Dan explained, instrumental metadata and imaging metadata on one side. That is, let's say, could be more formalized and fixed, and then experimental data, because each experiment is a little bit different. This is discussion, Thomas, you might remember. We also have all the time, what is really relevant to be described and then in what format. And I think now that Roland will give us another view, because dealing with omics data, things are also very nicely, let's say, organized, or not.
No, absolutely correctly. And I was listening to the trouble all of you have and coming into omics, as you saw with the presentation that Penny first was drafting and where we commented on and give together. Then the good bioinformatics protocol are there for omics. The complexity of omics, of course, is probably the driving aspect from the beginning, that you have standardized format to put it in databases, and there are all these workflows on how to work with it. I would, in that case, if you don't mind, invite Pekka if he wants to say something particular on how he stores various data. And then also, Penny, I've seen there been an intense chat dialogue about the quality and all of that. And I think she pushed here very nicely while all of you were talking that this reporting framework, which is now going to be formalized, covers aspect of quality and all of that was discussed. So, but if Pekka wants to say something, if that's okay for you, Damiana, then do so. I think it's good. And then Penny,
yes, of
because,
course,
we do this together from different angles. Please,
perfect. Pekka, welcome.
Yeah, hello. I'll start. I hope you can hear me. So basically, the omics data is there's a well-established framework how to store the raw data of omics. So you put it into EBI or the Gene Expression Omnibus biostudies or and so on. And but there isn't equally well-established framework for storing the biological metadata. So the biostudies and the EB and the gene expression omnibus does include information on biological and metadata, but I think, like somebody said, maybe Penny will elaborate on this. We maybe need to also put an entry for these data into eNanoMapper or something like that, which is more sort of toxicologically focused. And some other projects have made also their separate entries into biostudies when they've produced very large amounts of data, like some chemical risk assessment projects like the Risk CIRAT and Risk Hunter and so on. And then I suppose for the screening data, you put that into eNanoMapper and then you describe that according to the toxicological principles there, but maybe and the FAIR principles and so on. So these are sort of the ways in which bioinformatics data is stored in general.
Thank you, Pekka, very much. I have just one final question for you all. We have identified some challenges, and this is very much related very often to reporting, metadata, descriptors, and all the rest. My question is how you think or feel will artificial intelligence tools in the future help us, or how we should approach that we could employ these tools to make our data more reusable, of course, interoperable and all the rest, not to just, keep some data in silo and that could not be reused anymore, although a lot of work has been done and also good work. How do you feel? And where artificial intelligence tools could help? Asmus, do you have any ideas, or you already use or wait to be used?
Yes, I presented our work we did in this field. So we do the image segmentation using convolutional networks. This was necessary due to the irregular background our samples are deposited on. So these are Pohl filters that cannot be segmented using threshold techniques. So we developed this neural network, and it took quite some time. We generated a lot of annotated training data. I mentioned 20 gigapixels to train the network. And to be honest, we still do not know what it recognizes. So what it decides on to segment as a particle lying on the filter and on the filter. In the beginning, we thought we trained it exclusively on fibers, so to recognize fibers, shapes, but it can also recognize other particles. So one idea is it just learned to recognize the filter correctly, and everything which doesn't look like filter is then classified as foreground. We're also using these networks for interpreting spectra. This works pretty well, but of course you always have to be aware of the input quality of your data. We improve the network quality by adding noise to the training data, so to make the networks more robust with respect to low quality data, and we can check quite sensitively how the network performance develops. But these are very simple systems we are using. These are no large language models, also where we really do not know what you will get. And I think this very narrow field of applications, we really benefit from these neural networks.
Thank you, Asmus. I see the hand of Pekka. Just gone.
Yeah, I also I agree with people who said that, I mean, one of the problems still with AI is that it really sort of doesn't fully understand the, it's not there yet that it would sort of fully understand the data. So you need to structure it, I use ChatGPT, for instance, for writing code and also for some help in manuscript writing, and it can relate a lot of things to each other and gather and summarize information, but it doesn't have a sort of human level understanding or even approaching human level understanding of sort of common sense about the data that
Thank you.
the human has. So
we
maybe
need to
Thomas can elaborate on that, or Penny.
We need to help to elaborate such, intelligence to help us more in the future. Dan, what are your experiences with artificial intelligence now or in the future?
It is very good what Asmus has already started to explain. I can only continue, and maybe to put it as a big challenge. These AI or approaches, of course, are very good. We need them, but they are so specific. We have also our applications on titanium dioxide powders, which agglomerates or aggregates quite fine. But this is a completely different example from the fibers at all, of Asmus. And many probably will experience, will live this to see that we can transfer what we learn from a specific material to another one. This doesn't work. And coming then to 2D materials, to graphene, and very thin, again, a next challenge. I think it is necessary. Different groups are working on this. We have partial solutions, but the future, I am optimistic, will bring us more. Let's keep the pace, and we have to include the sample preparation, also very challenging point, which also must be included. So the measurement itself, I think, is not the problem, can be automatized and well controlled. The parts after image analysis and before sample preparation are something for AI. And
perfect, absolutely perfect. Good that we are recording this meeting, because in a year or in 2 years we could then go back and see in which direction things will go.
Janez, money if we don't get our goals.
Janez, what are your experiences at the moment? I assume you also have a lot of experiences because you also have a large data set, so you need to handle it somehow.
Yeah, we were, of course, very few of our parts of algorithms rely also on this kind of method, especially segmentation in the images. So we are aware of the very simple fact. These AI-like algorithms, you should use them explicitly where you can train them very well. You have data set with very low value of bad results in order to avoid hallucination. Normally, the AI algorithms hallucinate with exactly the same probability according to the training data set. So if there is something missing in the training data set, you just have to account on hallucination rate. And then the second huge problem is the contents base. So the AI works on pattern recognition in different spaces. The problem is that it doesn't create rules and it doesn't propagate these rules like physics-based. So, for example, you see that the particle aggregates. So you immediately switch on entire physics and physical chemistry rules that the surface is decreasing while particle aggregates, the interaction might differ, the scale might differ. So you intuitively take this into account. AI just draw the pattern and doesn't propagate that stuff, at least not yet. So basically, if you want to automate to make an algorithm that is well defined to a high throughput level, it's useful if you can train them without this bad result that would make AI hallucinate. Otherwise, it's I mean, for the rule determination or discovery, it's pretty very bad. Still very bad.
Thank you, Janez. And now words to Thomas. You're I would say final words, and then we ask also the audience what you think about IA, and in the future, how to handle the problems we are having right now with data storing, reusing, and so on.
You jumped me, Diana. Can I just say 1 second? Can I say one word?
Yes, of course. Sorry that I jumped you. Sorry for that.
I am
Sorry.
involved also. I wanted to just do the very quick one from what the head of AstraZeneca talked about. He said some words on that AI will not replace toxicologists, but toxicologists which use AI will replace those that don't. And of course but I do like that the hallucination aspect is very important to consider, and Pekka and now also Janez mentioned that I tried to put, and we did, an explainable AI concept in there, and that is important. Try to make it explainable, and the eye diagram was an example. The other short note is that going from supervised back to unsupervised analysis when you do training and validation is very complicated and essentially impossible in my mind. When you have a big EU project, for example, people need to speculate. They jump back and forth between the unsupervised to supervised. And if you would do a classical informatics AI analysis, you would first do the training and then do the validation. And that, of course, it absolutely never works the way I see it. But so we have challenges, but we can overcome them. And just finally, I mean, whenever we do anything with the high throughput data, omics data, there's always code writing. It's Pekka's fingers who knows how to do it. For every visualization, every analysis today, there is nothing which is not programmatically driven. That is a big issue to consider in the training of toxicologists and for the future, and how we have to work today. So those are just some comments. Thanks, Diana.
Thank you very much. Thanks. I'm really sorry because I put down you said, because it was so well summarized. Okay, and now Thomas, what would you add to this discussion from your point?
In principle, I now say the same thing. In other words, what Roland just said or cited. Yeah, because I think there is a difference between what you normally read in newspapers about what people think is AI and what we talked here as the useful AI. And I would call that, others also said, machine learning, because I think that is what we are doing. Or for me, there are big problems that this hype of AI is trying to go into extreme situations, and one is that perhaps people come to the idea to say, can I ask ChatGPT if benzol is, or whatever this material is, dangerous, and then there will be some output coming out from the AI, and it's completely useless because they don't have the information to do this judgment. That is the one point. The other point, which I'm a little bit at the moment careful, is really in data management, not in data analysis, data science, but more in we can just write papers as we always did, and then the AI will pick out the data points and will put it in a database. This is the wrong approach, because yes, we can try to get a value out of an XY graph, but it's stupid, because the data is somewhere and we should just take care that we structure it. And then we can use AI to help us to understand why. And this is, I think, a little bit back to what you, Diana, asked, how we know what is relevant. This is something we can ask AI, that you say, okay, these are all the parameters we have, which of them are really relevant? These are things which we can really use, and this is much better than a human person. Therefore, AI has very great application areas, but it's not the solution to everything.
Thank you. Thank you very much. Any quick final remarks from you or from the audience? Otherwise, I pass word to Blanca to give just the final conclusion. And it is all from my side. And thank you very much for all the afternoon speakers. Thank you. And Blanca, now the final minutes are yours.
Yes, hello. Thank you, Damiana. I have little more to report. I had prepared a summary, but I think it was more interesting to follow the discussion. I just would like to thank you, the audience, for staying with us for such a long time. I think it was a very exciting workshop. I really enjoyed and learned a lot. Also like to thank the speakers for really amazing presentations. And because I can already see on the chat that we start collaborating now with some of the people who gave presentations. So I hope these presentations enlighten the audience as well, and they find solutions to the problem, so they get people closer together. And I just wanted to give a round of applause to these great presenters and to the audience for the great questions that we had as well, and which allowed very nice discussion. Thank you very much, and we'll see you again soon.